Good morning to everybody. Welcome to the last day of our webinar series. It was a very, very interesting last 2 days, and we've learned quite a lot from the speakers up till now that on how to learn novice programmers programming, because we know all of that is very difficult to our people. We also want to thank the people that's involved in the organization of this whole series. I want to do it now because later today everybody will be tired. We want to thank Chris Tauta very much for his arrangements on the Facebook, as well as Dimbeka for all the arrangements, getting the Facebook set up, and the adverts for the webinar. Thank you very much to them. Then I also want to thank Dr. Bertie Buitendag, who helped so much with this whole arrangement of this whole event, also for the arrangement of most of the speakers. Thank you very much, Dr. Bertie. We really appreciate what you've done for the seminar. And then we're going to go now again to our most important speaker of the seminar, Prof. Raymond Lister. Prof. Raymond, thank you very much. He's all the way from Australia, and the reason why we're so excited to have him to talk to us is because of his time of more than 20 years of speaking on conferences and doing research in this specific area. We know it's one of the biggest challenges in South Africa to learn our people program, but now after this 3 days, we know it's not only in South Africa, it is actually all over the world. Thank you very much, Prof. Lister, and thank you for your time and that you are presenting for us. We are learning so much from you. I will just read his bio again, because I don't know if everybody has read the bio. Sorry, can I just ask you to take your cameras off for people coming from outside, please?
Thanks, Joey. You can continue.
Sorry, I was talking to myself. Prof. Raymond is the one person in the world that has got his papers in the top 5 working papers in 2 conferences in a row over the last 25 years. So he's the first author to have a paper in each of the lists that they see as a premier international conference and the best papers on the conference. So thank you, Prof. Lister, that you are lecturing to us. And it's now afternoon already there. It's morning with us. And thank you for your presentations, and you can start.
Thank you for that kind introduction, Joey. Well, what can I say? It's a pleasure actually to be speaking to you all, because although Joey's talked kindly about my record, I've spent most of my career working in institutions which were very focused on traditional research areas. So most of my colleagues spent a good deal of their time kind of looking out of the side of their eye at me and thinking to themselves, well, that's not really research, is it? And so on. So it's a pleasure to talk to you people who are interested in the same sort of problems as I am. Now, let's see. We have, let's see, I'm going to share my screen to start with. And then I'm going to bring up my PowerPoint. And then I'm going to bring up the program, believe it or not. And I shall ask the same question that Roxanne asked yesterday. Can you see my screen, everybody? Can you see the program for these 3 days on the screen? Not yet?
Not yet.
Let me see if I pushed the button, the correct button. Maybe I forgot to push the button. Let me try again. That one. Are you seeing something now?
Yes, thanks, Prof.
good. I'm glad I asked them. We could have got halfway through the talk before any of us realised that I wasn't showing the overheads. The reason why I wanted to bring up the program is because, well, let me explain. We have this schedule for today. Let's go back briefly to yesterday. The original plan for yesterday was that I would give a talk for about an hour, and then we would look at some questions in an exam paper and classify the questions according to Bloom. Now, unfortunately, my talk ran well over 1 hour, and that squeezed out the time that we were going to spend on classifying the questions into Bloom. And I know that's important for you people because you've got a lot going on with Bloom over there at the moment. So that's important that we get to that. One suggestion that I have is that I will talk about my stuff on Piaget in theory and teaching practice, or at least I hope to. But I thought I might invert the order of things today to make, with the permission of the organisers, I'm proposing this to them now and catching them on the spot. But I thought we'd start by looking at an exam paper and classifying some of the questions according to Bloom. And that way we'd be guaranteed to do it, rather than have me possibly run over time again on my own talk, and we miss out on doing that important process. So I don't know, unless the instructors dive in very quickly and shout,
you didn't record.
No, don't do it that way. We will do it that way. I heard somebody say something, but I haven't.
Sorry, the recording hasn't started.
Oh, okay. You'll let me know when it has started?
Sorry, did it start now?
And then we are 100% in order with this. Prof. Lister, as you can see, we've got 3 hours scheduled, so there can be some nice discussions and so we've got the whole time open. So that would suffice. Thank you very much, because it's a burning issue for lots of us, and we thank and we would like your inputs if you share some of the ideas. Thanks.
Okay. So a good thing so far is the stuff we've been talking about is organisational, so it doesn't really have to be in the recording. The other thing I'll say, Bertie, is I got your email with the diagram in it, and you want me to go through that. What I propose to do, Bertie, is people learn from examples more than general principles. So I thought we might go through the exam paper first,
yes,
and then look at that diagram, if that's okay with you.
No problem. It's just if we go through a paper now and you go through the diagram, we can contextualize it better. That is our yes. Thank you very much.
Okay. So I will just wait. That's the diagram that we will be going through. And then I will wait there until I'm told that the recording started.
It already started?
Oh, has it? Okay, right. Well, to the editor, I think I can say you could edit everything that's happened up to this point, and we'll start right now. So good morning, good afternoon, wherever you are. This is the third talk of my 3, and I'll be talking about 2 things. Oh, hang on, I'm doing the wrong thing. I immediately proposed. Let me get my head together. I immediately proposed that we were going to delay that. So let me delay that, and let me bring up the exam paper that I proposed to look at. A little note to the organisers. I did suggest that I might not do this one because I'd already annotated it, but I must confess that I'm feeling a little bit insecure about going through an exam paper cold. So I'm going to chicken out, and I'm going to look at this one that I've already annotated, and perhaps having the annotations in it will help some of the people. So the one I'm going to look at is one from the university for an introductory program subject. And of course, the acronyms don't mean much to me, but I'm sure they mean something to the people from that university. An exam they did back in 2020. Now, I made a little note. All my notes are in these yellow boxes. And what I do is, I've talked about this before, I tend to be an old-fashioned kind of a guy who uses the old taxonomy. And its ordering was knowledge, comprehension, application, analysis, synthesis, evaluation. The new one, which came out in 2001, made some changes. Some of the changes were to just the names of the categories. They changed from nouns to verbs because it's thought in education circles it's better to talk about what the student does, hence a verb. So knowledge is still the same. It's just known by new name, remember. Comprehension is the same. It's just now called understand. Application is changed from noun to a verb, apply. Analysis becomes a verb, analyze. The single biggest difference is here at the top, and I don't think it's a very big difference. The top two layers, the top two levels have been swapped over in the new taxonomy. The argument being that that creating stuff should be at the top. Okay, so synthesis, which was second on the list in the old taxonomy, is renamed creating, is promoted to the top, and evaluation is moved down to second place, because the people who did the revision felt that people should be able to evaluate something before they could create it well. And of course, in the process, they changed it from a noun to a verb. I think in most of my annotations, I use both terms. So that you'll find I use the old term followed by the new term, so that if you're familiar with one or the other, you should be able to follow it. That doesn't really apply here. My comments below assume that the reader has heard my previous two talks. Well, the odds are that if you're still with us today, then you have heard my two earlier talks. So let's move on. And by the way, organisers in particular, please, if you think I'm being too fast or something like that, please pull me up, slow me down. So here we come to question 1. Now, I'm very conscious that I've read through this paper already, and I've spent more time reading it that I'm about to spend reading it now. And that's a problem for you, because you might feel a need to go through the whole thing. We don't really have time to read every word, so I'll try to give you a summary of what I think each question is about. And if that's not enough, by all means, somebody should pipe up and tell me that they need to know more. But so the questions here are following. Well, the first ones are just, are they true or false? So an integer can be implicitly converted to a floating data type. Every Java statement must be terminated with a semicolon. A for loop is an example of a selection control structure. And then the next few are multiple choice with 4 options. So what is the importance of importing a class into an application? Blah, 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 blah. And one of those presumably is correct. What is the static method? I think I showed that on Monday's talk. That's one of the questions. Now, I won't go through, at least I won't go down through every single one of these. For question 1, as I've written in my comments, I think most parts of this, if not all, we'll get to that in a second, are at the knowledge level in the old terminology, or the remember category in the revision, the bottom category. Now, as I've written, you might reasonably argue that 1.4, this one here, goes beyond knowledge a little bit, because it asks what is the importance of importing a class. So you might argue that we're going that little bit further than knowledge, and we're asking the student to demonstrate their understanding of the significance of importing. I think you can make that argument, and I won't fight you on that, but I will stay with knowledge, because as I've written here, I suspect that remembering is the major psychological process involved here, rather than translating the question into some sort of a different form to answer it. I think it's mostly about remembering. But if you want to object, that's fine. I mean, it will come down to, we can follow definitions and tick them off, and that way we can arrive at black and white decisions. For example, if we agree that remembering is a major psychological process, then yes, this is a knowledge question. 1.4 is a knowledge question. If you want to debate that, I think you're free to, particularly as Bloom says this himself. You've got to remember that you're always applying this in a certain context, and you, the teachers, know what your students know and what they don't know, and therefore, on the basis of your superior knowledge of the students at this university, you might say, no, this is not a knowledge question, because we didn't really give them it in that form. It's comprehension. By all means, make those sort of arguments. I'm going to scroll down. If anybody, particularly the organisers, want to jump in at this point and want me to elaborate on anything to do with that, I can. I'm going to say that the rest of these are mostly, I still think, are categorized. What did I categorize everything as? Is knowledge. What is JDK, an environment? It is Java, and so on. I think that's knowledge. At least from this distance, it appears to be knowledge. As I've said, you might argue that it's a little bit different because of the circumstances of your teaching. I want to highlight this one. There's one piece out of 1.9. Peter has just learned about the concept of pre and post incrementing. He comes across a piece of code that displays the value of x as follows. And here's a print statement. The value of x is, if the value of x is 10, what would be the output? It's not clear here, by the way. I'm sorry, I'm being a teacher for a moment, not a researcher. If the value of x is 10, do they mean the value of x is 10 before the print statement or after the print statement? Slight ambiguity in the question, but I will assume that they mean if the value in x is 10 before the print statement. And I have gone with knowledge/remember again for this question. Now, as I've written here, you might argue that this question is comprehension, because technically you could say that realizing what's going on here is technically tracing the code. You can argue that, particularly if you know better about your teaching environment. But I'm going to stay with knowledge and remembering for this one, because I'll stay with that quote from earlier. Remembering is the major psychological process here. I think the thing that the student has to remember is what the auto increment does when it's in front of the variable name, and I think that's more knowledge than a tracing problem. My apologies if the exam writer is here and I've just critiqued your question by saying I thought that was a little bit ambiguous. My apologies, but we do that all the time to each other, don't we? It's almost cruel. So code reading exercises, question 2. And by the way, I remind you, particularly the organisers, if you want me to jump in and you want me to stop and elaborate on something, please pull me up. Now, Lutendo is running a small cinema business in Sosh. Please forgive my pronunciations, which I'm sure are all wrong. She only allows people who are 18 years and above entry into a cinema. Looking at the given code snippet below, which code is missing at A? Now, the thing is, okay, here's our code, and then there's a missing line here. And then crucially, we are not asked to write that line of code. We are asked to select from a series of options given to us. And on that basis, I'm going to argue that all the necessary information to answer the question has been supplied, and our job is simply to, out of the distractors, eliminate the distractors and choose the correct one. And that, for me, makes this a comprehension/understand problem. All the necessary information has been provided. The student's been given everything, including the correct alternative. I argue against, and I probably will be skipping over the other ones, which are very similar. Well, we might say a little bit about that in a second, but they're very similar. Something's missing, and it's a multiple choice question where you are asked to select the correct one. I argue against any having any of these parts. This is 2.1 and the others that I just scrolled down to briefly just now. I'll argue against having them at a higher level, since all the necessary information is provided explicitly, including the correct alternative. I mean, in theory, it's hard to, let's leave it at that. If the student has not been given alternatives, but instead was asked to write the correct solution for themselves, then that would be a question at the application/apply level. Now, unless anybody's going to pull me up and either tell me I'm wrong or tell me that they need to process this a bit more, I shall move down to the next part. I hear a microphone there. Is that just somebody happens to have the microphone on, or they want to say something? Nobody's speaking up, so it's just a microphone was on. Okay, this is the second one, 2.2, and I'm not going to say much about this because I'm going to classify it the same as before. We are given, in this case, 2 places where pieces of code are missing, and then we're given multiple choice options where we are given, the code that could go in those 2 places. Now, on Monday, when I talked about this, I said, probably you only really want to have 1 line of code missing, because as soon as you start talking about 2 and 3 and 4 and 5, eventually you must get to a point where it's just too hard. And so much code is missing, you're almost asking the student to write the whole thing. Yes, there is that grey area. How much missing code changes the nature of the question? I'm going to argue that in this particular case, with these 2 lines missing, it hasn't moved up beyond comprehension, particularly as in some sense the 2 lines are a little bit independent of each other. They don't interact too heavily. But so I'm going to stay with comprehension and understand for this question. Another issue, I think, which perhaps I could have added an annotation to, is there's quite a lot more code now. Some of it's, what some of us call boilerplate code. You've just got to declare various things. You've got to do some inputting and so on. So I'm going to argue that this code doesn't really, just sets things up, and it doesn't complicate the thinking too much about what's going on here and here. So that's my classification. I'm staying with comprehension understanding until you come for me with burning torches to tell me I've got it wrong. Once more, this is quite a lot of code, and I'll confess I haven't read through all this code. So if somebody has and they want to pick me up on this, I see one line missing. Is that right? And it's a while condition, and we've got to choose the correct condition to run this loop. So a lot of this code, again, is just setting things up, and the student doesn't have to process it too badly. They just need to understand, they just need to process what's going on in the while loop and why the while loop should stop. So again, I'm going to go with stay with comprehension and understanding. Now, I'm sure that if I tried to pronounce that name, I would get it wrong, so I won't. Best I could do would be AO, but I'm sure that's wrong. I apologize in public this time. I've done this before. For example, Bertie, I know I make a mess of pronouncing your name. I wish I could do better. AO wants to create a static method that will determine and return the sum of two numbers. Which of the following method headers is most appropriate? Interesting. They're method headers. So in a sense, there's no moving code. There's no code where variables are being, values are moving around. There's no algorithm as such. It's a header. And I would argue that means that it's not, reading this line of code is not really an exercise in tracing. Reading these lines is an exercise in applying your knowledge of what the various parts mean. Public doesn't matter too much because it's the same in every case. Clearly, some are static and some are not. So you have to understand what static means. And I know I'm using the understand word, but I should avoid that word. Maybe I should stick with in your knowledge base, you need to know what static means and what it means to leave it out. In your knowledge base, you need to understand what it means for it to be void, and or to return in, and so on. Now, you could argue that, the question has been set up here, and the student is being required to take this English level description and recognize the correct implementation of that in Java. And therefore, you could argue that there is a translation exercise going on from English to code, and therefore that puts it in the comprehension/understand category, the second lowest category. You could make that argument. And I've said if you use the same reasonings I've described above, you might put it into that category, comprehension, understand. However, I'm going to argue that I think, remembering is the major psychological process involved here. Not so much the translation from that to this. I think it's more remembering. But again, you may know better with your students and how they've been taught this stuff. And you therefore may want to argue that it's comprehension/understand. And I don't think I need to say, I'd just be repeating myself. I think if I talked about that one, it's substantially the same sort of issues as that one. Then we get to the IPO chart. And as I'll say in my comment, I'm flying a little bit blind here because I must confess I've never used IPO charts, either in my own programming or as in teaching. So bear that in mind as I offer up a suggestion on what's going on here. I could be wrong. So we have a triangle, and it's explained how the area and perimeter of a triangle would be calculated. And further down, create an IPO chart that will determine and display both the area and perimeter of a triangle. Given to you below is table 1. The table has possible answers that you can use to complete. Okay, right. So it's like a bit like a multiple choice question. We've been given a bunch of things and we need to choose It's not like we have to write the IPO from scratch for ourselves, which may involve some realizing certain abstractions are required. We're being told the alternatives. On the other hand, there's a lot of alternatives, and just being given them as a list may not be a big help. We'll see as we read a bit more of the question. Each possible answer is represented by a letter. Yep. So I think the student is being told, you don't have to write the whole thing, just write a letter. And then we come down to the part where the student has to fill in the correct letters. And I see that some have already been done for them. I think that's what that means. Or no, hang on, no, that's the variable name, is it? I shall butt out of that now in case I've got it wrong. But I think the student is required to write in all these places a letter corresponding to one of these things up here. Now, as I said, I haven't used IPO charts, so maybe I misunderstand what they do. I'm on the basis of what I do understand, I'm going to go for comprehension/understand. The student is required to translate or interpret from English to that IPO. And by dint of the fact that there's just so much information supplied, I'm going to say it gets a little bit beyond knowledge and it gets into the comprehension/understand category. And as I said, I'm prepared to accept that I may be wrong because of my limited knowledge of IPOs. Then we get to the flowchart implementation. And I've put my comment early, but let's go down through the question, then we'll come back to it. I think that we don't need to know too much about the actual problem being solved to do the Bloom classification. I did read through it, but I think that when I did my classification, but for the purpose of this presentation, I don't think we have to go through it in detail. I think what we do have to do is just admire the flowchart, if you like, and get an overall feel for how complicated the flowchart is. So there it is. We get down to a decision, and if this decision is true, we go here, and false, we go here. So we've got an if. This would be like an if-else condition going on there, and then we come down further. We have to go to the next page to see the rest of the flow chart. So we come back together after all that, and we do a couple of other things. And do you want to play again? And you get the answer. And if the person says yes, there's going to be a great big loop that takes us back up towards the start. So there are a few things going on. And I did say on Monday that definitely a simple flow chart is in the comprehension/understand level, and it's possible that a very complicated flow chart where you've really got to work hard at mapping from flow chart to these, say, nested conditions of code that could push you up. But I'm going to argue that this flow chart is not so complicated that it pushes it above comprehension/understand. Let's see if that's what I said. Okay, question 4, the flowchart question. Yes, I put it in a comprehension understand. The student is required to perform a translation. If you do remember Monday's discussion, I was very big on this word translation. If you translate from one formalism or English, so an unformalism, if you like, and you translate to something else and all the necessary information is provided, that just about guarantees that you're talking about comprehension understand. The flowchart is a well-defined form of communication that explicitly provides all the necessary information. It's a big flowchart and therefore a difficult comprehension question, but difficulty doesn't really change the Bloom level. And I think this is a problem that most people have when they first come to Bloom. You can have a difficult comprehension understand question. You can have an easy application question. Difficulty is a secondary consideration when it comes to assigning. In general, more difficult problems will rise up through the hierarchy. But sometimes questions are just difficult because they're long, they're difficult because they have a lot of detail. That doesn't necessarily push them up to a higher category. So that's what I'm going to stay with, because the flow chart supplies all the necessary information, and it's not an obscenely complicated flow chart. I'm going to stay with comprehension understand. You could ask me, well, suppose we made it more complicated. At what point would you move it up to a higher category? Well, I'd have to say to you that You know, you've heard the old expression, it's very hard to define the difference between art or pornography, but, you know, I know which one I'm looking at any one time. Likewise, I don't think that there are very general principles that will allow you to, with absolute clarity, apply with the general principles, and they'll always tell you, you know, what level you're at. Sometimes you've just got to look at the question. So I'm going to try to escape that accusation of just how much more complicated would this have to get by saying, well, show me a flow chart and I'll tell you. But I think it's too complicated. Problem solving. Okay, the problem statement. Two countries, A and B, are on the same timeline. The only difference is that one has a 12-hour clock and the other has a 24-hour clock. And then we're told to create an application that converts the times and allow a person country B to know what time it is in country A. You can probably stop reading the details at this point. I did read through it earlier just to make sure, but I think for your purposes, we can stop at that. We've got to convert from a 12-hour to a 24-hour. And then an example was given. You have to create the application, you, the student. So what did I say? I went for application and apply. So I've moved up from comprehension understanding to the next, into the middle layer. Remember that as far as I'm concerned, that, well, as Bloom says, the 6 levels form 3 pairs. So knowledge and understanding, those bottom 2 categories form a pair, and now we've moved up beyond those to the middle categories, the first of the middle categories, application in the old terminology or apply in the new terminology. So why not? And as I said on Monday, the middle categories tend to be defined in terms of how they differ from the other categories, from the bottom categories and the top categories. So that's why I've gone for a different way of writing now for this. Is why is it not comprehension? Because all the necessary information is not explicitly provided. I certainly haven't given an algorithm. So I don't think it's necessarily a complicated algorithm for how to do it. It's not like where the IPO chart stuff was given and so on. It's not a complicated algorithm, so I'm thinking this is not a difficult application/apply question. But nevertheless, I think it is application apply. It's a relatively easy application apply. Why not synthesis? Because I don't think that there's enough scope for creativity. If you're worried about this C word, creativity, just say, you know, you're marking the exam papers. How many qualitatively different correct solutions do you expect to see? So firstly, how many, you know, throw away there's infinite creativity for wrong answers. So let's ignore the wrong answers. Let's stick to just the right answers. Could you put them into a series of piles where you say, well, there's a few minor differences between, I'm holding 2 solutions. There are some very minor differences, but I regard them as essentially the same algorithm, the same thing. So I'll put them in the same pile. And you do that. So you come across another one, which is, well, actually, this one's quite different from the first 2. It's correct, but it's quite different. So I'll put it in its own pile. How many piles do you end up with? If it's a small number of piles, it's application and apply category. If it's a very large number of piles, in fact, if every solution is just about different, then you're moving up into the synthesis create area. Now, inevitably, somebody could ask me, well, you know, at what point? How many piles do you need before it stops being application and apply? And I shall say, you show me the question, you show me the piles, and I'll tell you. I'm not going to offer up a general opinion on that one. Oh, and then I put this, we had a debate about this on Monday, so I really should talk about this again. And I did kind of qualify what I initially said. As a rule of thumb, I suggest that it's difficult to give students synthesis create level questions in a written exam. This is the bit I added after Monday's talk. In a traditional exam like this one, where you've got students doing all sorts of questions, it's very hard, I think, to give them one that requires synthesis and create. But I agree with you after we discussed this on Monday. If you give students 3 hours to write a program, then it's fair to say that you could certainly ask a synthesis create question then. That seems quite reasonable to me. And I'll go back to my, different piles. If you took all the correct answers, you'll get substantially correct answers that the students gave you, and you started putting them into piles about how they differ, qualitatively. If you end up with a lot of piles, then it's synthesis/create. And then question 6, project coding. Koos, my apologies to anyone called Koos who might be listening. I'm sure I got that wrong. Is a property owner in Kempton Park. That part I can pronounce. He rents out his houses mainly to families because of their, okay, Koos wants an application that will help you anticipate the water bill, okay, for a house. Okay. Probably, I have read through the words, probably don't need to go through them. I think what we have to do is admire the complexity of what's involved in making the decision about how to price. It's quite a big table here. I can't say I've read every line of this. I just have admired the amount of detail in it. And it's on that basis. I haven't sat down and written a solution, so I could be wrong about this. On that basis, as I said, this is a tough one. I think I'll classify, having misspelled classify, it as application, apply, but with reservations. So again, I put it in the middle category, one of the middle categories. And generally, we define the middle categories in terms of how they differ from the bottom and the top categories. So again, why not comprehension and understand? Because I'll argue, at least from my understanding of what I have read in that table, that the necessary information is not explicitly provided. You might argue that Table 1 does provide all the necessary information, but I'm going to argue that it's provided in such a way that it doesn't map easily to a set of nested conditions in code. That's my argument based upon my reading of it. If you may have a better appreciation, particularly if you've seen a sample solution, you may have a better appreciation. And if you argue separately, I'm not going to fight you. I'm just going to stay with my conviction that mapping from Table 1 to the code is non-trivial, and therefore all the necessary information is provided. And therefore is not true, and therefore not all the necessary information is provided. Yeah. Why not synthesis and create? Well, as complicated as Table 1 is, I don't think it leads to a great deal of creativity in solutions. I wouldn't expect to see, if I put qualitatively correct but qualitatively different solutions into different piles, I wouldn't expect to see many piles, if any. But if you showed me the actual student answers from a class and there were an awful lot of piles, I'm not going to try to find how many crosses the threshold to be an awful lot, then I might change my mind. And then finally, I just repeated what I said in the previous question. As a rule of thumb, I don't think you can really ask synthesis and create questions in a written exam. And that rule of thumb has guided me to some extent in these last two questions. But I have conceded after Monday's discussion that if you have a 3-hour guys seem to have, you most certainly could ask a synthesis create question in that environment. And I think that was the last question. I mean, there's a great deal more information provided on how that one works, but I think the critical information was what I'd already been through up here. So that, I think, was the last question, wasn't it? Does anybody want to take me up either on any one question, or do they want to ask a more broad question that rises from looking at these questions? I'm just going to stay silent for a moment to see if anybody wants to speak up.
Batty, you can take the chats.
Yes. Prof. Lister, we had a question from somebody that asked, will difficulty be associated to the type of assessment? Meaning, should a class test be considered in the same level as, for example, in an exam? Or, yeah, that's basically, if you do a class test, the educational value of it, should it be on a more lower level class test, or should they also include more detailed type of questions? I hope I understand that question correctly, but I think I interpret it fine.
Okay, I think that the question is about the educational value of testing at different levels. I'll actually won't answer that question, I'll do a preamble answer first to a slightly different question. And that is, effectively, please understand I'm kind of deliberately misunderstanding your question for a moment. I'm answering a slightly different one. That is, the context, in a sense, doesn't matter. I mean, if you forget about the educational value of things, if you show me a question and I have to classify it, it doesn't really matter whether it's in a test in the middle of the semester or it's in the final exam. Oh, well, let's put it this way. If it's a mid-semester test, then the students know less at mid-semester than they know by the end of semester. So in that sense, you've always got to make judgments about questions on the basis of what you know the students know. So only in that restricted sense could a question potentially change categories between mid-semester and the end of semester. But in general, I don't think they do. So now let's get back to what I think the question was, as Bertie phrased it, and we might get. By the way, can I just explain that when I throw up my screen mode I can't see your chat window, so that's why I don't respond to you as you type questions. That's why Bertie's doing the good work of looking at them for me. So the educational value. I'm tempted. Well, let's take my researcher hat off for a second, and even my Bloom hat off for a second. I don't want to speak with authority on that issue. I just want to speak as one colleague to another, one teacher to another. I think that we want to, and we're talking about the mid-semester, and let's say it counts for very little. We have to make it count for a small percentage of the final, score of a student at the end of semester. It has to count, say, 5% to their final grade or whatever, because otherwise the students won't do it, or they certainly won't try to. So we attach that, but as teachers, we know that 5% is neither here nor there, really. And so we're effectively doing it as an exercise in helping the students to learn or encouraging them to learn. So what's the best sort of questions to give in that situation? Well, you said the word test, I think, in your question. I can't see the chat window, so I can't verify that. You said a test, so I'm going to say you're not setting anything at the synthesis evaluation level and what is a relatively small test, I think. My view of those sort of tests is that they have two functions, is to help the student learn, and the other one is diagnostic. You get to find out where the class as a whole is, and where individual students are in their learning. So I would be inclined to give a bunch of questions, if it's possible, if you have the time. Certainly at the comprehension, possibly at the knowledge level. I usually never have many knowledge questions. So I usually start at comprehension and understand. Certainly there, and certainly at the apply application level. Maybe if I can think of something, I'll do something at the analysis level. And I'll have a range of questions so that I can get a spread and see where the class is. Usually the sad truth is that you find out that everybody's down at the comprehension level, and you have very few students. Mike McCracken's Picasso's might be up there doing the other ones, but the great bulk of your students are down at that comprehension level. Is that an answer to the question?
Yes, I think it is, and it's wonderfully stated. Our next question that we have is, if we look at the missing code fractions, then the person asks, I suppose the more code in these instances raises the difficulty level, not the cognitive level. And I think that's something that you really emphasize, Prof. Raymond, is that there's the difficulty level and the cognitive level is two different things. And linked to that same question, there was somebody that asked, is there something like Bloom's taxonomy for determining the difficulty level, or a combination thereof, or something like that? I mean, we did look at the solo taxonomy, but anything in that regard?
Yeah, okay. The difficulty, I will say I'm not sure. It's the short answer. I'll suggest somewhere you might go to see if it would help, and that is the revised taxonomy. The original Bloom's taxonomy is this one-dimensional set of levels, the 6 levels. And I'd have to say, and this is not a criticism of the revision, I think that the changes made on that dimension, the changes to the names from nouns to verbs, the switching of evaluate and and create are not that important. But the really substantial change / addition that the revision, the revising people made was they added a whole second dimension where for each of these levels, they then go on to talk about, it's like a table. Imagine, I can't bring it up, but I'm sure that one of you can find it when you do some Googling. You've got a table where as you go down the table, you move through the levels as we know them. And then across the page are a series of columns with titles describe cognitive processes that students have to do of different types for a problem, potentially for a problem at the levels that we are talking about. That might be a good place to go. Let me try to, apart from the fact that I think the changes to the names in the dimension that we are talking about was more, for me, it's more of a nuisance than anything else. For you guys who've learnt Bloom after 2001 and you've learned it from the revision, no problem. But for an old fogey like me who learned it before then, I'm never sure which set of words to use. I think better than the old one, and then I have to translate when I talk to people who know the revision. What was my point? Oh, and I've found that over the years, as you people are finding, it's hard enough for people to come to a consensus on these 6 levels, how to classify questions into 6 levels. So I just put the second dimension of the revision in the too hard basket for myself. I've not worried about it for that reason. However, well, there's another reason, but I won't go into it. You guys who are really worried about this issue of difficulty, there in the revised taxonomy in that second dimension may be the answer to your problems. I don't know, because I don't know the second dimension very well, but it's worth looking at. I think that's all I've got to say about it.
Thanks. And then we've got another question. Does multi-select question qualify as an attempt to raise the difficulty level? Yesterday, we spoke about types of questions, and Prof gave it a specific name where we had that type of ordering and multi-select type of questions. So the question is, does these type of questions attempt to raise the difficulty level?
So I'm sorry, I think you were quoting me just then. I think Bertie's having said something yesterday, but I'm not clear what it is that I said. What do we mean by multi-select? Is that like where you've got a series of lines of code and you have to put them in the correct order? Or is that something else?
That's one of them. And then the other one is selecting all the possible options that could apply to a particular term, to a particular concept. So it's like a multiple choice question. And Hannes can come in here if he wants to speak. It's like a multiple choice question where there can be more than one particular correct answer to the question, but it's not just limited to 4. It can be 7 or 8 different.
Oh, I see. Okay. Again, of course, to give you an authoritative answer, an answer with great conviction, I'd say, show me the question. But let's talk in general. In general, if we're talking about a multiple choice where there's more than, say, 4 or 5 options, 4 or 5 is very typical. Let's just for argument's sake say there are 10 options. I don't think that changes the level. I still think somewhere in those 10 options there are 9 distractors and there's 1 correct answer. And you are putting a cognitive demand on the working memory of a student, I suppose, by getting them to sort of compare questions and decide how they differ, and options and decide how they differ, and then eventually arrive at the correct one. But I don't think that issue changes the Bloom level. That's my suggestion on that.
So it's my question. May I ask something about that?
Sure.
I've had many years of asking multiple choice questions and that type of stuff, and I found that the pass rate goes down the moment I change my multiple choice to multi-select. Even in my multiple choice, the moment I add a none of the above, all of the above option, then the whole ball game, it's as if it changes for the student. And there is an observation of a drop in pass rate, should that not be seen as a difficulty level incline?
Well, I'm not going to answer with great conviction. I think I've seen something similar. I know what you mean. I used to add none of the above. I used to have what I thought were one correct solution, three good options, and then I'd add as a fifth option at the bottom, none of the above. And the principal reason why I did it is because if I made a mistake in writing the question, then none of the above usually meant that I could salvage the question. So that's a very pragmatic reason for doing it.
But that's with one correct answer. Multi-select means there's more than one correct answer. So it's a combination of answers that makes it correct.
I won't answer with great conviction, but I'll put my hunch to you, which is that multiple choice questions are quite effective, but there is considerable scope for game playing. Where a student doesn't really know the answer, but they can apply certain principles, certain heuristics to give themselves a fair chance. Like you can almost always eliminate one option. It's just a bit silly. The examiner ran out of ideas for distractors, and there's one that's a bit silly. And there's all sorts of other ones that you may know of. When in doubt, go for option C, because there is a psychological tendency to bury the for people writing questions, to bury the correct answer among the distractors and not have it at the top or the bottom. Sometimes it's the longest answer. There's all sorts of ways that students can gameplay the system, and exams are like a Turing test. We ask a series of questions of the student, and then we listen to we read the answers to decide if there's any intelligence involved in the answers. I say that slightly facetiously, but I think it is a good comparison. And so in the Turing test, the computer is trying to fool you into believing that it's a person. Equally, the student in this game is trying to convince you they know something when they don't. And so the game playing, I think, is why you see your scores going down, because the more options you offer, particularly if more than one is right, if you add things like all of the above and none of the above, I think you make it harder for some students to play the game. But I don't say that with great conviction. That's the best I think I can do, as one colleague to another.
Thanks.
How does that sound to you? Or would you disagree? Oh, and I should add, to actually specifically answer your question, because I think it's mostly about game playing, I don't think it changes the Bloom level. Sorry, how does that, do you want to disagree with that and just say a few words, or?
I don't know. At the end of the day, we use Bloom to determine the overall ability of the student to answer the questions and how difficult they will find it to attend. So I don't know. I can't always separate the method from the cognitive part and just say that is, because it's not. Otherwise, the marks would have been the same. I don't know.
Neither can I, honestly. Neither can I. I know I'm speaking with great conviction over these days about Bloom, but there are times when I look at things and I'm not sure. Actually, I mean, it's interesting to go back and think about what Bloom was up to back in the beginning. Bloom, we're talking about back in the 1950s, and Bloom and his co-workers on that committee, they were firstly focused upon kids in primary school. I think you call it primary school in South Africa, or elementary school in America. Kids, up to about 12 years of age. They were focused on them. That's what they wrote the taxonomy for originally. And secondly, Bloom's motivation, if not the others, was, whenever he went looking in the 1950s or in 40s in schools, he found exam papers which tested the students on facts. Facts. What are the three types of rocks? Igneous, sedimentary, metamorphic, or something, okay? And what he was trying to do with the taxonomy was make teachers aware and examiners aware that there are high-level things that you can ask about. So what Bloom was arguing for was a diversity of questions to be. He was encouraging people to come up with a diversity of questions, to test the full range of abilities in students, and to make the questions a little bit more relevant to the real world rather than just a dry set of facts. Now, why talk about that? Because firstly, Bloom was very focused on kids in primary school up to about 12 years of age. It's not immediately obvious then that the taxonomy carries directly across to undergraduates at university. It seems to work, but I think sometimes we have to understand that issue and then use that, be guided a little bit by that when we're trying to place students into or write questions for our students. And the second thing is, I think you said something about the purpose of the taxonomy was to gauge the ability of students. And I suppose that's correct. But again, I'd go back to Bloom. The real purpose of the taxonomy is to encourage the examiners to write a variety of questions at varying levels, at the different levels, so that there's a range of things being asked and that we get away from dry, very factual-based stuff and move into more sophisticated problem-solving type questions. That was a long, rambling answer. I'm not sure I actually addressed the comment you made. I hope you got something out of that. I suppose, actually, I'll go back to what I said. Bloom had his own purposes back in the 50s. The trouble with people like us, and I mean computing people, using something like Bloom is that we in our work, in our day-to-day computing jobs, we like things to be precise, to be unambiguous. Now, Bloom's taxonomy is not designed to be a computer program, to be an algorithm. There is some fuzziness, and we have to accept that as computing people when we apply it. Don't get too carried away with the fuzziness. But, I tried in my answers to sometimes say, well, look, I think it's this and this is why, but I can see why there might be an argument that it's something else. I think you've got to try and be precise as much as you can, but there will be some disagreement. There will be some fuzziness. Put it this way, form a committee of 3 people and the correct category is what 2 out of 3 believe.
Prof, we've got another final question that came up. Somebody made a comment and says, my belief is that the student can be asked questions requiring and operating on a synthesis or create level if they are required to make choices in terms, for example, of how a screen layout should look like. What is your opinion on the upside down Bloom's triangle, where creating and evaluating and analyzing is on the same top level? That was the comment and then the question. It's from the
same. Where the creating and evaluating. So the let's see. So is there 2 parts there? There's let's start with the user interface one. That's a good point. I think that you could ask, if you read the original Bloom book on the synthesis level, you'll find that he spends quite a bit of time talking about essays. Because they weren't talking about computer programs back then. They were looking for something where that related to the students, kids at those times. So writing an extended essay where they were arguing for or against something was the sort of thing they had in mind. Now you could present a user interface to the students and say, evaluate this user interface. I think that probably is a question you could put in a written exam. Quite a good question. However, just bear in mind that in the description of evaluate, at least in the original Bloom's, it says it's not just, the student is not just expressing an opinion. An evaluation is done against some criteria. And now, of course, there are very good criteria for designing user interfaces. So if the student just wrote us an essay where they said, I like this interface, it's very colorful, it's got this, that, and the other thing, I like that, that's not evaluating. If the student takes some evaluation set of criteria that you've given them and they apply that in their essay to answering the question, yes, I think that is an evaluation question. So I shall have to add another modification to what I've been saying about the written exams and say that, yeah, you can ask one about user interfaces. Could you also ask one about, say, the decomposition of a problem into modules? You know, could you present the student with a heap of code and then say, tell me whether this is this program has been well modularized. In theory, that would be an evaluation question which you could ask. I'm just not sure I could fit it into my exam. The student would have to read so much code. I'm not sure that it's practical, but in theory, that could also be an evaluation question. Now, that was the first thing you said about user interfaces. The second part was, I'm afraid, Bertie, you might have to remind me what the second part was. It was the last.
The second part of the question, what is your opinion on the upside down Bloom's triangle, where creating and evaluating is on the same top level and analyzing?
I'm very comfortable with that. I mean, I must confess I'm a bit confused by the upside down bit, because when you said that, I just imagined the entire pyramid, all 6 levels inverted, and I thought, well, that doesn't sound right to me. But you're just talking. I shall answer this question, then you can tell me I'm answering the wrong question. The issue of the top 2 levels being swapped, I really don't mind that at all. I'm very relaxed about it. Bloom himself said that although there are 6 levels, they form pairs, and he was very relaxed about the exact ordering. In fact, maybe what he should have done is have, the words in each pair on the same line. So there's actually only 3 levels in the taxonomy, and you've just got what remember, understand on the bottom, then you've got apply, analyze in the middle, and so on. Yeah, I don't mind anybody. If you have the cognitive skills to say apply well, then you probably have the right cognitive skills to analyze as well. Probably. I mean, I could get into performance versus competence models, which is a concept I don't think we want to get into today. Did I answer the question, or did I answer the wrong question?
Sorry, Ron here.
Yeah.
Good morning. Good evening. It's about the create, evaluate, analyzing be on the same top level. So the pyramid looks like it's upside down with a wider top and a narrower bottom, where you actually put create, evaluate, analyze on the same level.
Create, yeah. So create, evaluate,
and analyze is at the top level, above applying and all the rest to the bottom.
And then everything else is below that.
Yeah, and it seems like it's narrow at the bottom and broader at the top. But we use the Bloom's taxonomy where those 3 levels are actually compressed into one level at the top level.
Okay. I would, I'm the classicist in a way, aren't I? I'm the one who reads the Greek, the original Greek, and then argues with people about something. So I'm reading the original Bloom. And I object to putting analyze on the same level as create and evaluate, because by the definition of Bloom, he goes to some pains in the document to say, analyze is a more modest activity than evaluate. So, for example, I think I expressed it on Monday this way, which is, again, thinking in terms of pairs. The analysis process is performed upon, say, a piece of code that the student could have potentially written at the application level. Think of it another way. A student writes the answer to a problem at the application level, and then the solution is handed to another student, and that student analyzes it. And we're not talking about, is this a good user interface and so on. We're talking about, well, let's leave it at that for a second. There's not much scope. The analysis is mostly about correctness and so on, issues like that. When we go up to the higher category, the emphasis in create is very much creating. There's a tremendous richness to a diversity to what students could produce. And therefore, the evaluation is much more sophisticated. It's not about right and wrong. It's about evaluating the choices that the person made when they created this thing. And furthermore, like I said a little while ago, the evaluation is done against a defendable and established, if you like, set of criteria. It's not a simple judgment about right and wrong. It's much more complicated than that. So I object to that inverted curriculum, I guess, given what you've said.
Thank you so much.
Yeah, I'll digress slightly. Well, I don't know if it's I'll extend. I'll run away with that a little bit. I keep saying that they form pairs. I like that because I was told decades ago by psychologists who worked in that area that if you want people to classify something into categories, he said, don't have more than 3 categories, because people just don't reliably categorize. Groups of people do not reliably categorize to the same category when there's more than 3 categories. And I wish I'd written down the citation that the guy gave me at the time, because it's something I've come back to many times over the years. I feel very comfortable with reducing Bloom down to the 3 pairs, because then I feel comfortable with where I place things, much more comfortable. Once you have many categories, people never agree. That's the end of that little digression.
Sorry, I didn't see another question, and we're already now busy for an hour, so maybe we can make a 5-minute break before we start with the next presentation. A 5-minute body break.
Okay, sounds good to me. So it's where am I? It's just clicked over to 6 minutes past the hour here, I think. So say
yes.
6:11. Yeah, 11 minutes past the hour. Okay.
Yes. Okay.
I'll talk then.
So we will have
Bye-bye.
a 5-minute break and come back. Thanks.
Okay.
Hello, everybody. I think everybody's back now. Prof. Lister, I think we're back now, and I think we can continue.
Prof. Lister, if we think you're muted.
Yes, I was, Bertie. Thank you. I'm now not muted. So we shall carry on. Now, the next agenda item was not to go straight to a talk, but Bertie asked me to look at a diagram he produced, which is this. Now, when I say produced, actually what happened was that I have sent to the organisers some scans. Now, hang on, where is that? That document I scanned. Oh, yeah. A series of pages, 7 or 8 pages from the excerpts from the original book, which were in the 40-year retrospective book. Now, this is the scan that this is from the scan that I sent, and then Bertie produced a high-quality version of it. Now, however, Bertie, I think there's a copy and paste error in your production, which is you've got immediately leaving familiar aspects, immediately having familiar aspects to guide students, immediately having familiar aspects to guide actions. Oh, no. So the same thing, I think, in both boxes, isn't it?
Yes, it's a copy, paste, and paraphrase error. So we will fix it. I will fix it in that regard and send it out again.
Am I sharing the screen still? I'm not sharing the screen, am I?
Yes, you are not now. I will quickly fix it, and then we can share it from that one. I'll do that just now.
You can. How about would this work, Bertie? In the interest of, can I just go to my scan and just work off that? Or?
Yes, no problem. That's fine.
And you're seeing that right now, aren't you?
Not yet, no.
Not yet.
Seeing the chat screen, the interface off. So maybe just share the screen again.
I'll try. Am I sharing the screen now?
Yes, that's fine.
And people are seeing a page which starts with page 22, excerpts from the handbook. Is that right?
Yes.
Good. So Bertie wanted me to go through, and I'll confess, Bertie, and you shouldn't be embarrassed by this, that I think I'm about to be embarrassed because I've never quite understood this diagram. I know these very violent annotations on the are mine. So fairly clearly I've spent some time looking at this, but I'm not always sure that I understand what it's trying to tell me. So particularly amongst the organisers, if it's speaking to you in some way, feel free to pipe up as we go through this with your possibly better interpretation. I relate better to the words in Bloom's book than this particular diagram. So a problem is presented, an exam question is presented, and then I think this is key. It comes down to, I've talked a lot about, we haven't talked about it. Let's see. Then the question is perceived in one of two ways, if you like. It seems to be unfamiliar is one of the possibility, which would lead the student to trying to find bits that they do find familiar. And then otherwise it's immediately obvious that it's familiar. It has familiar aspects to guide actions. So then we move down. So let's move down to here. So staying with the familiar, some restructuring by student to make resemblance to familiar model more complete. Okay, so I think the point that Bloom is trying to make is that, it doesn't, some work may be required by the student to turn into something that feels familiar. And then initially unfamiliar, there's a process the student has to go to where they the student uses familiar elements to restructure the problems in a familiar context. And then they come back together again. So I think what we're saying is, what's the student's initial reaction? Whatever, one of two things, but nevertheless, the student has managed by either of these processes to arrive at a point where they feel that the problem they're being faced with is of a familiar type. Now, I wrote over here, as you can see in my annotation several years ago, application starts here. I'm not sure what I meant by that. So I should leave that out now for the moment until I figure it out. Maybe I will as I go through more of this. So then, selection of abstraction, theory, principle, idea, method suitable to problem type. Now, I'm not sure why I drew that. This application starts here. I don't know why it's so high on the page. Right now, I'm thinking that actually that annotation should be down here. Maybe it was meant in a sense to be down there in the sense that it was talking about everything above that big thick line. Here's the crucial step in application. The student had to make a selection of an abstraction, a theory, a principle, an idea, a method to solve the problem. And that's the key difference from comprehension or understand. All the information was provided in the comprehension understand question, whereas here the crucial step, this might be why the application starts here, the crucial step happens where the student must make a decision about what theory or principle idea they're going to use to solve the problem. And then I said here difference comprehension starts at step 5. I'm not sure why I wrote that. So Bertie, in your change, maybe you should take out my annotations. I'm not sure what I mean by them now. If they speak to you, keep them in. Use of abstraction to solve the problem. So the student has made the selection, and then they've solved the problem using that abstraction, and they have their they start to solve it and they solve the problem. So there's the diagram. Anybody want to comment upon that? Let's start with the organisers. Any comments, guys?
From the chat, Ronnie commented on use the, I don't know if it's Cinefin or Sonofin mode. Maybe, Ronnie, you can just elaborate a little bit more.
Yes, it's Cynefin. It's a Welsh word meaning family. If I can share my screen, then I can quickly show it to you, and then maybe we can use that to understand this diagram a little bit better.
Okay, I think I've stopped sharing, so you should be able to share.
Okay, so this is Snowden, and we extended on it in a recent article that me and a colleague published. So these are the different quadrants that we operate in. So once you are confronted, there's a kind of a disorder where you don't know, it's this one, 0, which is this little block here.
Mm-hmm.
Let me see if I can quickly just add this, and it's easy for me to. Sorry about this. This area here, where you don't know in which one of the spaces you are confronted with this uncertainty. Then you have to decide whether it's known, whether it's chaotic, whether it's complex or noble. And then there's a set of best practices for each one of these ones. So in the known one, you'll select the best practice. In chaos, you will have some trial and error type of action. In this one, you will have a fail-safe experimentation, and in this one you have critical thinking. So if one can apply this to that diagram of yours, I think it might be easier to understand how it flows.
Okay, so we put that diagram that you said. Well, actually, we've got a little problem now, haven't we? We probably need both.
We can't share
picture.
both, yeah, unfortunately.
Yeah.
I will share this with Joey, and then she can send it to you or something like that.
Okay.
I think that is a good idea, Ronnie, that we can just put it next to each other when it projects. While you're sending it, there's Donald also wanted to contribute, so we will just give Donald a chance to contribute while you send us that diagram that we can share it together next to each other by Prof. Lister. Donald, you can talk.
That might have been an accident, sorry.
we have a comment. In looking at the original or the diagram, doesn't it mean that for comprehension, the first steps are provided as we look in those steps in the diagram? And that is how we understood it, as I also understood it when I've gone through it.
Ah, that sounds familiar.
I think it comes.
That sounds very plausible to me, because I think that's how I was. Did that come about because not only did you look at the diagram, but you were reading the text at the same time? Is something that?
Yes, yeah. and I think you mentioned it. I can't put my finger on it now. In one of your previous articles as well, that it is like a flow. But don't ask me to pull it up now.
Okay. Yeah. Okay. So, where do we go from here? Are we waiting for something where the two things we put together? By the way, if we're going to do that, I shall warn the person who shared that diagram that they are going to have to talk about the relationship between the two diagrams, because it's their. I'm still processing their diagram. I wouldn't dare attempt to relate their diagram to this. They will have to do the talking.
Now, I think, Prof, you can continue with your normal, the type of presentation, and we can take questions at the end again. And then later on, we can maybe arrange like an informal discussion where we can sit with Ronnie, because it's obvious that he's also done some wonderful research, and then we can discuss it in an informal manner at a later stage. And then Ronnie can share it with us again. So let you continue with your presentation. And then Ronnie says, that's fine. So then we listen, and you can continue as you planned.
Okay. Right. I'm going to share the screen, or attempt to. And if I've done it right, you should be now looking at a page which has a wonderful picture of some good-looking man, and then it says at the top, talk 3. Is that what people are seeing?
Yes, Prof.
Good. Okay, a little. So talk 3 was advertised as following, as having Piagetian theory and teaching practice. To some extent, it should be Piagetian theory and also teaching practice. So there's sort of kind of two parts. They're related, but they're somewhat disjointed. And we'll see how we're going. I mean, I noticed that we're now almost at the half-hour point, half past the hour. If I give this whole talk, it could last an hour, which may leave less time than the organisers would like. I could just do a portion of it and leave the rest. How about I start, and we'll get to the hour. We'll get to in about 35 minutes, we'll get to the top of the hour, and maybe then the organisers can decide for themselves whether they've heard enough of me or whether they think I can carry on. So let's get going then. So talk 1 was the early stages of my career and the development, a lot of it before I actually started doing research. And then I became this research evangelist in my middle years, and I talked about that yesterday. And I guess I remained the evangelist in my latter stages of my career, and that's what I'll talk about today. A lot of this actually is not till 2020. It's probably stopped around 2000. We'll stop with Donna's thesis, really, and Donna Teague's thesis, and we'll get to that shortly. So where did we finish yesterday? I made this connection, but that we didn't have to approach research and teaching as two separate worlds. We could combine them, and I'm not going to go through all that. I just want to remind you of a saying that I've had on several slides yesterday. A good exam, or any other assessment item, but a good exam should teach you something new about your students, and what you learn that's new from your exam or your other assessment item should then be used to drive change in the subject in the future. And yesterday, actually on Monday and yesterday, I went around this cycle 3 times, and I won't go through a detailed summary of all 3 again. I think I'll just remind you of what had happened by the end of the 3rd cycle. By the end of the 3rd cycle, we were talking about this sort of data analysis where in a final exam, some colleagues, Anne Venables and Grace Tan, put some exam questions into their final exam, some questions which involved tracing and some questions that involved explaining. And we wanted to see how students' performance on those two types of questions predicted their performance on writing. I shouldn't use that word. In what way is tracing and explaining related to writing? Do they correlate? And I asserted yesterday that that's a really good fit. And I won't go through the entire defence, but I'll just point out again that nobody who did poorly on both tracing and explaining, none of these students down here who did poorly on tracing and explaining did well on writing. And equally, nobody who did well, nobody who did well on tracing and explaining did poorly on writing. So on that basis, this is really a different diagram representing the same thing. We were arguing by the end of that work that somehow, some ability to trace code and some ability, when I say explain, I mean, it doesn't have to be an explaining plain English question. It could be any technique you use to establish that a student understands a piece of code. So, but I use explaining because that's the sort of questions we use. So if a student can trace the code and if they can demonstrate some ability to understand a piece of code, if they have those two skills, it tends to predict quite well whether they'll be able to also answer writing questions well. Now, the issue in those first 3 trips through the research cycle was that although we did some, I like to think was nice empirical work, putting questions in the end of exam papers and so on, there was no real theory guiding us. It was just our gut instincts as teachers, very experienced teachers, and I'm not taking all the credit for this. There were some very talented people in the group. The idea of an explaining plain English question came from somebody else. The specific one that we used a lot, the code that checks to see if an array is sorted, was suggested by somebody else again. So I'm not taking all the credit for what went on. But there were good guts involved, people with good intuitions about their teaching, and that led us partly by luck, experience, good intuition, and some luck to use good questions. But the trouble with relying upon that all the time is, and no real theory, is that your luck will run out. Your intuitions will run out. You need some theory. And as Kurt Lewin said a long time ago, there is nothing so practical as a good theory, because a good theory will help us guide us asking our next question and driving our next, next few trips through this loop. I should say this, it's not that there is no theory. Really, everybody's walking around with a theory in their head. They're just not aware of it. You've always got a theory. You're always being guided by a theory, but you just don't know what it is sometimes. So what I'm going to do is I'm going to talk about the 4th trip through. And this is where Donna Teague, my ex-PhD student, and I applied Neo-Piagetian theory. One thing that's not clear here is that neither Donna nor I invented Neo-Piagetian theory. It dates back to the 1980s. We read about it, we liked it, and we applied it to programming. We were the first people to apply it to programming, or at least in this form. Furthermore, I'm so aware that my talk ran over time yesterday that I'm going to try to, I could talk for several hours about Neo-Piagetian theory and how it applies to programming, but I'm going to try to just give you a taste. I'm not really going to talk a lot about it. Just give you a taste. So here, there's a picture of Donna, my former PhD student. She submitted her PhD thesis. There you see Neo-Piagetian theory and novice programming. She submitted that in 2015. So the theory she used was Neo-Piagetian thinking. And the empirical method was think aloud. Somebody, I think yesterday, asked a question. They said, you've got all these quantitative results. What about qualitative research? And my answer to them was, well, wait till tomorrow. And here we are. Yes, we'd got some good results by sitting down by putting questions into exams and then sort of interpreting at a distance, looking at the exam paper and thinking about what we thought that said about the students' thinking. Well, Donna went much more direct and much more qualitative rather than quantitative. She went and sat down with students and had the students think aloud as they solved these problems. And it was on that basis that Donna and I were able to map what we were seeing in the students' thinking to Neo-Piagetian theory. I have to address an elephant in the room in case there are some people with a good, strong education background out there. The odds are that you've been taught in your education about education that Piaget is dead. Well, Jean Piaget is certainly dead. He died in the early 1980s. But furthermore, his theory is dead. And it's certainly true, and I'm not going to go into the details, that significant portions of Piaget's theory are now discredited. We Neo-Piagetians, and remember, I didn't invent Neo-Piaget. I am now a converted Neo-Piagetian evangelist, but we Neo-Piagetians believe that we've salvaged all the good bits and we've thrown away the bad bits. And I could talk for a long time about why some things are good and why things are bad. I'm not going to. I will make one very important point, which is in classical Piagetian theory by Jean Piaget. He's talking about the development of kids. So he talks about how kids reason at 2 years of age, how kids reason then change at around 7 years of age, how they change again at 12 years of age, and so on. That's not what neo-Piagetians do. What we say is, no, it's not really biological. It's not only biological. It's not the developmental stages of a child. What you see in the Piagetian stages is something you see when a person of any age learns something new. It could be computer programming, it could be chess, it could be anything. You will see these levels. And I'll show you what that means in programming in just a second. If anybody's still very unhappy with me, what I'm trying to do is show you that I am aware that Piaget has its critics and its good critics. If people still want to debate that with me, we'll do it another time, please. Okay, so here are what we call the 3 stages of novice programmer, and here I'm using the 3 terms straight out of Piaget. The student goes through 3 stages of learning to program: sensory motor, pre-operational, and concrete operational. I'm not going to go into great details about how I justify mapping these from Piagetian literature to programmers, but I'm going to summarize the mapping I've made. And that is, students in the sensory motor stage can't trace. And furthermore, their approach to programming is just incoherent. You must have had the experience of sitting, you're just looking over the shoulder of some student as they try to write some code, and it's just incoherent. You cannot see a thinking process as you watch them, change their code. There just doesn't seem to be any sort of thinking process behind it. There certainly are students, particularly students who can't trace. I mean, if you can't trace, you can't do anything. Your approach to programming will be chaotic. You may be pleased to know I'm not going to say much more about tracing today. I'm going to talk beyond that. The pre-operational are the ones that really Donna and I found most interesting, and that's what I'm going to talk about mostly. These are students who can only trace. And like the person who has a hammer, every problem looks like a nail to the pre-operational student. Every problem in programming is solved by tracing code. I'll elaborate upon what I mean by that shortly. I just want to talk about the 3rd level. And the concrete operational level in Piagetian words is basically how most of we teachers assume that students think. And certainly for the first 10 years or so of arguably the first 15 to 20 years of my teaching, I thought students thought the same way that I do about code. And I was wrong. I eventually learned through all this research that I was quite wrong, that all students think the same way that I do. That there's these other 2 categories of how students think about code. And I won't say much about that 3rd category either, because that's the sort of assumptions you already make about your students. And here's the preview, the takeaway message, and that'll frame everything else. The key idea that comes out of this Piagetian thinking is that we assume that students, there are 3 stages, and we assume, however, in our teaching that students really start at stage 3, or effectively they move so fast through the first 2 stages, sensory motor and pre-operational, that they end up almost immediately thinking at stage 3. And so we talk to the students the way we think about programs. We, the teachers, talk to the students in our lecture series about how we think about a program. And for all the students, and that's fine for the students who are at that 3rd stage, but for all these students in the lower 2 categories, we might as well be talking to a foreign language, and in a strong sense we are. They don't understand our language. They haven't got to the point yet, where the 3rd stage, where they can understand our language. Now, what am I doing? Piagetian theory can be confusing, and one of its unnecessary ways for it to be confusing in this talk today is that these 3 words, I don't want you to end up spending the rest of the talk struggling to remember these 3 terms: sensory motor, pre-operational, and concrete operational, and what order they occur in. That would be a cognitive load you don't need. So I frequently use 3 other words to describe these 3 stages, and here they are. Well, not words, but terms. I talk about pre-tracing students. They can't trace. They haven't learned to trace yet. I talk about tracing students. The only thing they can do is trace. And finally, I talk about post-tracing students who've moved on from, they can still trace, but they've moved on to reason about code in a more abstract way. Now, I've discovered recently that as convenient as these 3 terms are, pre-tracing, tracing, and post-tracing, I've now found that when I talk to people, they forget Piagetian theory entirely, that this has origins in Piagetian theory, and they just think purely in terms of those 3 things. And some of the things I'm going to say will be assertions that don't make sense unless you remember that I'm drawing them out from the Piaget and theory. Okay, so pre-tracing, tracing, and post-tracing can't be too hard to remember, I'm pretty sure. Well, I hope so. So I'm not going to say very much at all because I've hammered to death the pre-tracing students on Monday and Tuesday. You know, I just remind you again, and maybe you should stick this on your wall above your office, above your desk. You know, we did this multi-institutional study with 12 universities, 7 countries, lots of students, and an awful lot of students were scoring. Half the students were scoring half or less on our 12 multiple choice questions. They can't trace, they can't do very much at all. That's all I'm going to say about those students, I think. In fact, because I wanted to shorten my talk, I think, yeah, I've done this. I put some big lines through some of my slides. It's the last thing I did before we started today's session, to say to myself, Raymond, don't talk about this. You've talked about this enough. I could talk for hours more about this, but I'm not going to. I will, however, break the rule for one thing. I would like to compliment James' presentation yesterday on many things, including his use of these tangible things like cups and so on. Students who can't trace need these sorts of props to understand how programs work. So nice work, James. That's all I'm going to say about that. I have talked about this before. It's a lesson that students, even at the end of high school, and for that matter, even at the end of first semester at university, cannot solve, well, many students can't solve very simple tracing problems. So I'm going to skip that. Phew, well done. I got past that, and now I've got past the students who can't trace, and I want to talk for a while about the students who can. But here's the key, and this is what only came from knowing Piaget literature, neo-Piaget literature, and Donna's Think Alouds. I didn't know these students existed until Donna came into my office and started talking about them. By this stage, you know, I'd been teaching for 15 years. And I didn't realize this was going on in my students just from my teaching. It was only when Donna sat down with students and had them solve some problems by thinking out loud that I began to realize that this was going on amongst the students now. Okay, before I go any, there's an anecdote comes to mind, a quick one, which I must tell you, because I want to advocate for doing research again. And that is, you know, I've said before, particularly yesterday, you know, sometimes you've got to take a step back from your teaching and you've just got to watch the students. And from what you observe, you learn something new about them, and that improves your teaching. The trouble with being a teacher all the time, it's not exactly trouble, but, you know, a teacher will always intervene to teach. And when Donna started her Think Aloud work, I had to sort of coach her for a while because she was a teacher of many years' experience. And as soon as the students started to get off track and answer the questions incorrectly, Donna, the teacher, would jump in and correct the students. And I would listen to the tape recordings that Donna had done of her Think Alouds, and I'd be listening away, and I go, no, Donna, no, Donna, you can't stop the student and correct them. We're here to observe the student. Now, at the end of the Think Aloud hour, if you would then want to be Donna the teacher and correct the student, by all means, but for that hour, you must just listen to the student. Don't teach them, just listen and observe. And from her listening and her observing, I learned something about my students that I hadn't learned for 15 years, after 15 years of teaching. So these are students who can only trace. And I want to illustrate that by talking about a student called Donald who did something that we found fascinating and astonishing. So this is the problem we gave Donald. In one sentence, describe the purpose of the following code. Do not give a line-by-line description. And I'm going to work you through it so that you understand the code. This is not all the code. We're going to add some in a second. So if y1, a variable called y1, is less than the value in y1 is less than the value in variable y2, and then we didn't give the student code because we didn't want them worrying about how a swap worked. We just gave them the pseudocode effectively. There would if this if condition is true, then there would be code to swap the values in y1 and y2. That would go there. So if I asked you to describe just that code, and if we were in a room together, I would at this point stop and insist that somebody tells me, just if nothing else, to wake up the room. No disrespect intended, but I'm a terrible audience member at most presentations. I kind of switch off very easily myself in many presentations. So if we were going to describe what that code did, there's an answer. It rearranges the values, if necessary, rearranges the values in y1 and y2 so that the smallest value is in y2. Okay, so the smallest value is in y2. T to be in y2. Now I want to focus on this bit of code, which is almost the same as the previous code, but instead of y1, y2, it's now y2 and y3. Same idea though. If the value in y2 is less than the value in y3, swap those two values. So if I now ask you what happened as a result of executing those two if statements, your answer might be it rearranges the values if necessary so that the smallest value of the three values is now in Y3. And I've left out because I didn't want to fill up the slide too much. Of course, the other two values are in Y1 and Y2. But bottom line is I'll give you full marks on the exam paper if you said it rearranges the values so that the smallest value is in Y3. And then finally, the last piece of code is a repeat of the first piece. So we've compared Y1 and Y2 and if necessary swap the values. We've compared Y2 and Y3 and if necessary swap the values. So we now know for sure that the smallest value is in Y3. And then we compare Y1 and Y2 again and swap them if necessary. So what are these three if statements doing? They're sorting the values. On the exam paper, if you just wrote it sorts the values, I'd be happy. We didn't care because it was exam conditions and people make all sorts of mistakes in exams. We didn't care whether you suggested it might be from lowest to highest or highest to lowest, or we didn't say either. We were just happy if you saw the forest and not the trees and you said it sorts the values. It's a kind of a bubble sort on three elements, really, three values. Now, this is not a trivial problem, we discovered. At my university, I put this question into a mid-semester test, so after 6 or 7 weeks of learning to code, and half my students got it wrong. They didn't give me an answer like that. They couldn't give me an answer like that. Now I felt bad about that, but I felt better when we gave the question to a set of students at another university, and at this point I shall very quietly say it was Donna's university. Donna was a teacher at a different university. And this was in their end of first semester exam, at the end of semester, and 2/3 of her students got it wrong. So this is not a trivial question. If you're worried about the way we framed it and do students understand what's really required of them, let me just tell you that we went to a lot of trouble to make sure that students did understand. I'm not giving you everything. I'm just trying to fit something on one slide. So there's extra stuff not given. Also, we gave students questions prior to the exam to practice questions, which include this. So they should have been well aware of what was required of them. So what we just did, working through that code and coming to the answer that it sorts the values, is what I'm going to say is a post-tracing reasoning process. We didn't read the code with a specific value in mind for Y1 and a specific value for Y2 and a specific value for Y3 in mind. We read the code in an abstract way. Being experienced programmers, we were able to say, if you execute that code, then the smallest value will be in Y1 after it. And if you execute all of it, the smallest value will be in the values will be sorted. We didn't think in terms of specific values. So it's not tracing, it's post-tracing. You might argue that in a sense what we did was tracing. In a very abstract way, we were tracing. We weren't so much keeping specific values in mind in Y1, Y2, and Y3, but we were keeping sort of constraints in mind. We knew that after we'd done that, after the first line, there was a constraint on the value of Y2 that it must be smaller than the value in Y1 or equal to, for that matter. But let's not get into that. So you might argue it was a very abstract form of a trace without specific values. Okay, that's fine. If you want to call the post-tracing stage the abstract tracing stage, that's fine. But nevertheless, they're not tracing with specific values. And I will describe what we just did as a deductive process where we figured out what the code did by just reading the code. A deductive process. It turns out that the tracing, by the way, for any Piagetians who are out there or Piagetian critics, what I just did was an exercise in transitive inference. That's how Don and I dreamt up this problem. It's transitive inference. That will mean something to any Piagetians out there. Don't worry if it doesn't mean anything to you. Now, the tracing students can't do that. They can't reason the way that we just reasoned. They have no other skill other than tracing. And as I said, like the man with a hammer, every problem is a nail. If the tracing is the only skill they have, they cannot abstract from the code itself to reason at a higher level. They will attempt to solve a problem like that one by tracing. And that's what one of Don good research practice, Donald adopted a pseudonym for the lengthy set of studies that he did with us. Here's how Donald went about the problem. There's the code, exactly the same code as before, just now shortened so it's on the left-hand side of the page. This is what Donald did. Donald said, Y1, Y2, Y3. He initialized them, to the values 1, 2, and 3, and then he commenced to trace. And I will point out, I will boast at this point that when Donna and I devised this question, we gave the variables the names Y1, Y2, Y3, because we were hoping that some student would do this, initialize the values to 1, 2, and 3. Okay, and then Donald did a perfectly well-organized trace and quickly and efficiently, and he correctly traced to establish that the value in Y1 at the end of this would be 3, the value in Y2 was 2, and the value in Y3 was 1. A correct trace. But here's the fun part. Donald is not a post-tracing student. Donald is a tracing stage student. He cannot reason from code. He reasons inductively from the values. He started with 1, 2, 3 in his 3 variables. He finished with 3, 2, 1, and he could have made the correct deduction from there, but he did not. His induction of what this code did was the following. It reversed the values in those three variables, Y1, Y2, Y3. Not that it sorted them, it reversed them. Now, I remember when Donna came to my office and said, "You'll never guess what Donald did." And I listened to the tape, and Donna and I sat around for quite a while going, but that's amazing. For example, I can remember I said to Donna, well, to begin with, if all you're doing is reversing values, you don't need if statements. So why does he think the if statements are there? And furthermore, if you're trying to reverse the 3 values, you don't need to worry about Y2 at all. You could just compare, you could just swap Y1 and Y3, which is in fact not an operation that we offered here. So all up, pretty clearly, Donald is not thinking at a post-tracing level. He's not really thinking about the code. He's thinking at that tracing level where purely deductively he's doing that and coming up, because we constructed it this way, he's coming up with the wrong answer. We wanted to find out if there were students who do this sort of thing. Now, a little side note, I should have had something about this. I talked about explaining plain English questions and how you can use them to study students and what they know. If you're putting explaining plain English questions into your exam, be careful that the student can't figure it out this way by tracing, by picking 3 values and just tracing and then inductively figuring out what the code does. Well, you can do that, but what you're really trying to do with an explaining plain English question is give them code which works at the post, where they have to reason at the post-tracing level to figure it out. If you go back to the one that I looked at yesterday, where the code checks to see if an entire array is sorted, you'll see that the odds are that you will not figure that out just by tracing some random values. You need to think harder about the code. Okay, so that's what Donald did. I don't know if you're surprised that Donald did that. I was astonished. And this is more than 15 years after I started teaching. Now, during talk 1 on Monday, Tanya, and I will not mispronounce the rest of her name, Tanya said in the chat window, "I've taught learners who were terrible at coding, and later on they've become programmers in industry." Yes, Tanya. In fact, this is a digression in a sense. Yes, Donald, in fact, went on to work in industry quite well, as a matter of fact. He was regarded by his teacher at the time as a student who was not doing well in the programming undergraduate course. But Donald went on to work in industry. And the moral of that story is, with some students, teachers need to be more patient. Oh, furthermore, you don't move a student, but give them developmentally appropriate learning tasks. What I mean by that is, if you give a student like Donald, who's at the tracing stage, a large program to write, or even a small one for that matter, they don't learn anything. They just resort to bad programming practice, and I'll show you some bad programming practices in a second. They don't learn anything as a result. You've got to give tasks to the student that will help them develop from the tracing to the post-tracing stage. And it's really only when a student gets to the post-tracing stage that you can expect to see them write code using a sort of a coherent thinking process. Before the post-tracing stage, their approach will be somewhat chaotic. So, yes, Donald went on to work in industry. We need to teach more slowly, be more patient, and in particular, we need to give developmentally appropriate learning tasks. If we just write a program to do X, write a program to do Y, and if that's how our teaching is done, the students at those first 2 levels will never progress to the 3rd level. The 3rd level students will be just fine, but those other 2 levels are stuck. Now, for the tracing stage student like Donald, there is little or no abstraction beyond the code itself. All Donald and others tracing stage students can do is trace code and then make inductive guesses, if you like, about what the code does. And bear this in mind, because now when you go into your lab and you look over a student's shoulder and you see them doing bizarre things, you may understand why, because they're like Donald. They don't abstract. They don't see the bigger picture, the abstract picture. All they see is executing code. Now, programming by random permutation, I left that word out. This is such a well-known thing that somebody felt they needed to have a Wikipedia page about it. This approach sometimes seems attractive when the programmer does not fully understand the code. Happens in industry, so I'm told as well, but I'm more focused on students. I certainly see no end of students randomly changing their code because, in fact, they don't understand the code. Related to that is shotgun debugging. They've written some code and they've run it and it doesn't seem to work. So because if they're reasoning at that tracing stage, if they haven't moved up to the third stage, well, they have no way of debugging their code beyond making some relatively undirected changes and hoping that eventually they'll get it right. And for very small problems, 5, 10 lines of code, maybe they do get it working. But it's a process that will not work as they move on to more larger exercises. Voodoo programs is a favorite term of mine. Even if the program works, the student does not understand why it works. I've certainly had those encounters. I've had students come to me and when I ask them about their code, it turns out that even if the program works, they don't seem to understand it. And in my early years of teaching, well, actually until relatively recently, I just assumed if a student had a working program and they couldn't answer some simple questions about it, that they obviously got somebody else to write it for them. And maybe they did. I'm not eliminating that option. But I now know that, in fact, particularly on small exercises, the student might have got it to work, but they actually may not understand why it worked. I mean, if enough monkeys type long enough, eventually they'll type Hamlet. And if a novice programmer keeps typing long enough, eventually they'll get your small programming exercise to work, but they won't understand why. Oh, a little detail. I know maybe I could skip over this. How am I going for time? Not bad. Not bad. Maybe you don't need this. This might be more for the people who know Piaget. One of the problems with classical Piagetian theory is Piaget talked about those 3 levels: sensory, motor, pre-operational, concrete operational, which I'm mapping to pre-tracing, tracing, and post-tracing. And there's always been this worry in classical Piagetian theory about how do these students appear to make these quantum leaps from one lower level way of reasoning to another? Why does a 7-year-old suddenly switch from one sort of reasoning to another? Are they struck by lightning, or what is it? Well, neo-Piagetians think they have the answer. And it's rather than sudden quantum mechanical like transitions, the students are steadily making changes. That is, I've drawn time on the horizontal axis. When a student starts out, they may move very quickly to more sophisticated ways of reasoning, but every student, the first instant they're exposed to programming, they're in the pre-tracing stage. That's their dominant activity. That's how they don't understand how code works. They can't trace it for that reason. For all sorts of reasons, students can't trace. So, but as they begin to learn some stuff, that sort of pre-tracing behavior, errors in tracing and errors in reasoning about programs, misconceptions about how assignment statements work, how while loops work, and so on, they decrease with time. And the second type of reasoning increases, so that eventually the dominant way that the student thinks about things is what I call the tracing stage, like Donald. And then as time goes on, hopefully, particularly if you give the students developmentally appropriate learning tasks, if you throw them in the deep, if you throw Donald and other tracing students in at the deep end with lots of writing of quite sophisticated programs, they'll not progress beyond this stage. But if you give developmentally appropriate tasks to the students, they will eventually rely less on tracing their code and more upon reasoning about the way that you and I do, and they will move to that post-tracing stage. So you can see students in your class that clearly fit into those 3 categories, but you'll find lots of students also who are not easily mapped into those 3 categories. Donald, at that instant we caught him for that Think Aloud session, was very much a tracing student. Yeah. So the 3 stages of the novice program. can't trace, can only trace. That's the ones that we've been talking about. I want to make you aware of this, the students who can trace but they can't do anything else, because I think they are the neglected category. We are aware that students can't trace. We are aware that students have misconceptions about how an assignment statement works or a while loop. That's well known. But I think this is not so well known, that there are students who don't have misconceptions and so on, but they can only trace. They haven't really abstracted yet to how the code works. Which brings me to the conclusion to part one at the top of the hour. This is brilliant. 3 stages of novice programmer. Well, I'll just leave that there for decoration. I've been talking about it for half an hour. I don't think there's much to add to that unless when I hit the space button, something else comes up. Oh, it does. Teachers commonly assume that novice programmers start at stage 3, or at least get to stage 3 easily and quickly. That is not the case, at least for some students. Perhaps many students do. I'm in no position to put labels on, what percentage of students are in these various stages. I suspect that this is the tracing stage students, and well, that matter pre-tracing, but let's stick to tracing. I suspect there's a lot of students in most classes who are at this stage. But the reason why a lot of students are at this stage is not because of anything to do with them. It's because we're not giving them learning tasks which are intended to move them from that stage to the next stage. If you ask students at this stage to write large programs, they will go about it in a very bad way, and they will not really learn much. And they'll just stay there they'll just stay there. By the way, Donald went on to work in industry. I have to say that I think Donald went on to work in industry, because he got into our research program, and Donna did. After she'd spent an hour talking to Donald and watching him make a mess about things, she would then spend teaching time with Donald afterwards and say, no, Donald, this is what you're doing wrong, and explain it to him. And Donald did eventually go on, and I don't think he would have in the traditional undergraduate program at Donna's University. I don't think he could have gone on to become a programmer, because the traditional undergraduate program wasn't catering to a student like Donald. Now, that is, if you like, the first half of talk 3. And I can go on to talk about teaching practice, which, let me say, is related to Piagetian theory, because you may see the influence of the Piagetian theory and the idea that there are tracing stage students who have problems. You may see that, or you may not. There is a connection in my mind, maybe there isn't. But this is the point where I shall ask the organisers, should I carry on? Let me show you before you have to make such a call.
Sorry, Prof. Can we just do questions on the first talk before we continue?
Absolutely. Before we do that, absolutely, that's a good idea. I'll just give you an indication that is slide. Okay, so I'll be starting at slide 38. No, sorry, 38. And what I have, if I go through all of them, don't necessarily have to go through all of them, is well, that's the last one really. So 48. There's another 15 or so slides. So that's for your information. But no, let's go back to let's take the questions then.
Okay, Prof. One question we've got is, what are some of the tasks you mentioned to help the students move from stage 2 to stage 3?
Yeah. A lot of patience and repetition, I think, is what you've got to do is as they perform a trace, you've got to relate the trace to, say, a diagram of what's happening in the code. Well, for that matter, it could be, it could be paper cups with numbers in them, as was being demonstrated yesterday. So you've got to relate the code they're looking at to the to that abstraction, that symbolic simulation, if you like, of the code. And you can get them to do it. I mean, you can say, okay, you've just changed, you just executed, successfully traced this line, in the code. What did that do to your, what did that do to the values now paper cups, or they then have to do that. Now, to be precise, when I talk about stage 2 and stage 3 programmers, there are people who can trace code. Yep. And even many of those people, if you show them the simulation, if you give them a bunch of things and say, sort them into order of size, they can do it. So in that sense, they understand at an abstract level how to sort. But what they can't do is connect the abstract level, the physical thing they just manipulated, to code. It's that disconnection between the two that we're working on. And what I've done many times with students, particularly when they come to me with buggy code, is we sit down and we have a sort of I pick up a few items off my desk and I arrange them. If it's a sorting algorithm, just to give a simple example, and we work through their code line by line and say, okay, what did that do to the objects sitting on my table? Move them to show me what that line of code just did, and then I say to them, is that what you wanted the code to do? So that's the primary one. It's practice at seeing the connection. Yeah, don't take it for granted. And you might say, well, in my lectures I do that all the time. I have diagrams on my slides, and I show. Yeah, but hang on. Just because we do that at the front of the lecture theatre, I know this is. I'm not being patronising. You know this, but there are people who don't know this. There are people not attending who don't come to seminars like this who don't know. Just because we say something at the front of the room doesn't mean students understand it. And furthermore, you need the students to manipulate the symbolic constructions themselves. It can't be you doing it at the front. It's got to be them doing the manipulations and somebody telling them whether they got it right or wrong. That's the best I can do right now. This is actually a pretty open area. Improving students in this area, I think, computer unplugged, the unplugged stuff, and also, I know CS Unplugged from the person in New Zealand who does a lot of it. I'm not sure if it's close related to what goes on in South Africa or not. That's great stuff. I like it. Don't get me wrong. I don't like it. I do like it. But if I go back to this for a second, a student can possibly manipulate, a CS Unplugged exercise, right? Like sorting values or something like that, right? And they might be able to trace code that does the same thing, but they don't actually quite see the connection between the two. And that's what you've got to work on, is connecting the higher level picture to the code. Long answer. I hope it wasn't too long. Anybody else?
It's a long answer, but a very good answer. Prof, there's not specific another one in the chat, but there's somebody with a hand. Brandon, you can ask your question.
Sorry, can you hear me clearly?
I can hear you. Yeah.
I'm an IT teacher in a high school, and I'm just from my personal experience when I did IT at school. I tell my students, like, there's a thing, like, sometimes in programming where I call it the aha moment, when it all clicks. And at school level, like, we in grade 10, 11, and 12, like at grade 10, 11, I struggled to get that aha moment. I literally got it late in my final year of school. But what I did to survive in the subject was to look at the parts that I like to get the marks, or to be able to do things that I could do. So like the theoretical aspects, I focused on that just to keep me, like I tell the students, to keep me in the game. And so what I try to do with a lot of particularly my weaker students, is I try to tell them there are what I call recipe codes. There are things where you can learn particular recipes, and those are the algorithms, like your sorting algorithms and so on, that are that the kids can at least see how that works, and they can play around with that code. It's like if you were learning to cook. You don't learn how to bake. You don't experiment straight away. You first start off with generic recipes of how to do a scone or how to do brownies and that, and you learn like that before you start experimenting with your own styles. So I found, particularly with my weaker students, just to give them to still ignite that love for coding, to see that I made a computer do a sort. Even though they use someone else's code technically, but for them to see that, and then they can play around with that. So I feel like for our weaker students, I often use, as I said, like a recipe code that they can at least see how it works. They can like play around with it. They can still dabble with coding until they get that aha moment where it starts to make sense.
I agree completely with you. In fact, you've just cheered me up tremendously, because I was heading into this second section on teaching practice with a little bit of trepidation, because I think what I'm going to present is not fashionable. In that I agree with you. I give students quite a lot of code, and I get them to know it. But that sounds like rote learning to many people, and I will talk about why I think you can avoid rote learning. But I agree with you absolutely 100%. I mean, what you've got to do is, there are three things. The students, first, the student's got to be able to trace. You've got to get them to the
Yeah.
point where they can trace. You've got to fix the misconceptions and so on. There's no point in really showing them any code until they can trace. Okay. Then you can also show them the high level algorithm where they do it, like CS Unplugged. They put objects in front of them and they manipulate the objects. So they understand the algorithm. But the third thing is what we take for granted. We think that students relate those two things, the code, which they can trace, and that high level simulation. They don't. It can take time for that to happen. And the best connection that I can think of in education literature in general is the literature on reading. Kids learning to read. There are kids who can stand up with the book and quite fluently read you a paragraph or a page, and then they can't tell you a thing about what was in that page. If there's any teachers who used to teach in primary schools, and so they will be aware of that, I think. And this is exactly the same thing. There are students who can trace code, but they can't really tell you a thing about what the code is doing. Okay, is that an answer? We've agreed.
No.
This is
Just
wonderful.
just a little comment. Yeah. I understand the whole concept of road movement. Just for a lot of my students, like for the weaker ones, just to give them the time that they need to get that aha moment, like just to play around with it, just to get them there.
The aha, I agree with the aha moments. I'll go back up. Am I still on screen share? Can you see my overlapping waves again?
Yep.
Yeah, I almost gave you a second slide after this, but I decided it might be too much information. But now that you've brought this up, this whole idea of aha, I think the neo-Piagetians might overstate slightly the overlapping waves. I think that what goes on is, I was going to have a picture of a kettle. You turn on the kettle and at 70 degrees, 80 degrees Celsius, 90 degrees Celsius, you've got water. At 99 degrees, you've got water. But suddenly at 100 degrees, the water starts turning into water vapor, right? You get what's called, the physicists would call a phase change. And I think we do see that some of the times for students. The aha moment is when suddenly they stop being predominantly pre-tracing and they switch. There's this moment where it all comes, as you said, it clicks. The pieces suddenly come together and there's a phase change in the way they're thinking. So yes, I believe in aha moments too.
Cool, thank you.
Anything else?
No, just a comment. Thank you.
Great.
Thanks, Prof. We also just got one comment. It might also differ per topic. That means depending on the topic, things might change. Do you want to comment on that?
Absolutely. It's a good point. If I was talking for much longer about Piagetian theory, we would talk about the Piagetian principles of assimilation and accommodation. So that sometimes, I've taught you for a week on integers, and we've talked about is variables, and we've moved integer values around amongst integer variables. Then I come back in next week and I present you with floating point numbers. And really, there's still values moving around between variables. I'll give you very similar tracing problems to do, and there's no difference because there's a difference in that we're now working with floating point numbers, but the principle of how to trace and so on hasn't changed. But then sometimes concepts come along which disrupt your way of thinking. And an obvious example that most people are aware of is when you introduce loops, suddenly students' ways of thinking about code kind of break and they struggle for a while. Sometimes things move smoothly and then sometimes there's a real break and a change. Is that what the person was getting at with the question?
I think so. I think that is what it is, that sometimes it's not that easy to do it that way. But in that case, if we look at what James showed us yesterday, I think that was a very good idea to show students how the changes are. It is a type of tracing, if I'm correct. It is type of tracing, but more visual than writing down.
Yep.
Then thank you very much. I didn't see any other questions. Can we take a 5-minute body break before we start with talk 3?
Sure. Okay, 5 minutes. That'll be 15 minutes past the hour.
Correct.
Okay, 5 minutes. See you then.
Thank you very much, everybody. We're back again from the break, and Prof. Raymond, you can continue.
Okay. And during the break, I facetiously changed the title to Talk 3.5. So that's the end of Piaget in theory, at least very explicitly. I think there might be a slide with the Piaget towards the end. But I'm going to talk about teaching practice. If you don't necessarily see the connection right now, I think there is. Maybe it's my imagination. That won't matter too much. Okay, right. And if you like, frankly, I didn't have time to do a very nice set of slides. So I have copy and pasted portions out of a paper I wrote and published in 2020 on the cognitive development of the novice programmer, which you can find at that URL if you find this stuff interesting. So my apologies for the very heavy text-based next few slides, but I'm sorry, but I just ran out of time and couldn't do better. Okay, well, before I get to my own pages, I just want to mention something called mastery learning. What I'm going to be talking about is a little bit like mastery learning, but I'm not going to say much more than that about it. You can watch I recommend a very nice TED Talk by Sal Khan. The URL's there. If you don't recognize Sal Khan, you've probably heard of Khan Academy. He is Khan Academy. And he gave a talk at TED called Let's Teach for Mastery. And what he was saying was very pithily in a lovely polished 10-minute talk. So, a more general case of what I've been saying in the case of programmers. In the case of programmers, I'm saying that we just don't teach the basics very well. The students then move on to higher level tasks and they fail at them because they don't know the basics. And the analogy that Sal Khan uses in this video is, imagine if we built houses that way, where we pour the concrete for the foundations and somebody come in and inspect it and say, well, that's a pass. It's not great. It's not a great set of foundations, but I'll give you a pass. And then you build the first floor, and then you start putting the second floor on the house, and everything falls down. And people say, well, the builders couldn't build the second floor right. Well, no, the problem was that the foundations weren't right to begin with, and that's why the whole thing fell down. It's a nice talk. I recommend it. I'm going to illustrate one thing I do to take a lot of it might not be obvious from this presentation, but I believe one of the reasons why this works is it takes a lot of the abstraction out of arrays early and allows the students to see them in a much more concrete way. So I actually introduced arrays in week 2. We did until my retirement. And here's an example in Java of if you can't read Java, don't worry about it, but it's just initializing an array which has 2 elements, 5 and 7, and in the next line I assign a new value to the first position, A0. And then we talk about what that means. Students have done a very similar set of tracing problems in week 1, where we don't do it with arrays, we do it with scalar variables, just integer values. So this is not a strange absolutely strange thing to be doing, but we get to start talking about arrays. The crucial thing, of course, is that in this example, I've used a constant subscript. And in week 2, I only use array scripts that are constant. I think one of the things we do is we move to using variable subscripts almost instantaneously in teaching arrays. This is giving you a preview of where we're heading. And, if I had here not A0, but AI, where I is some integer variable, that's quite an abstraction for a novice programmer to think about. The ith position of the array, it's a very general idea. They need something more concrete, or many students need something more concrete early on. And here's an example of a piece of code we kind of go through where I have arrays in weeks 2 and 3. Down here, this piece of code shifts elements of the array one place to the left. And you see it's all hard-coded. We store, and we're going to wrap around the leftmost position. So we store the value from A0 from the 0th position in a nice safe place, and then we shuffle all the others across, and then we take our temporary value and put it in the right-hand end. And I showed people, by the way, I should have put this here. We trace that to understand that. And then having traced it, I will set a little example problem for students to work on. Okay, now you know how to do it to the left. See if you can write it so that it goes to the right. A lot of students can't. But that's not the issue. I mean, we're just letting some of the better students exercise themselves by giving that a generalization. But I showed them a few examples like that. Bottom line is they all have constants. And I'll give you a little preview. Well, actually, I don't say this explicitly later on, so this is probably a point worth making. One of the standard problems that novice programmers have is remembering that sometimes the code is talking about a position, a value in a certain position, and sometimes the variable's referring to the position itself. And I'm sure you've seen many students with their code where they confuse those two things, a position in the array and the contents of that position. Now, when you use constant subscripts, I find there's no real confusion. That goes away. And we introduce students to the concept of an array in a way that doesn't lead to that confusion. A couple of weeks after they've done that, they then are introduced to one of their first classes in Java, and this class is what I call a list of 4. It maintains a list of 4 numbers. I haven't shown you here the private data member which does that, but it's just an array called list which takes 4 integers. And okay, it returns a number of times the value in val. So we're searching through this thing called val. We're searching for the value in val occurs in the 4-element array. We're counting how many times it occurs. Val contains the value to be counted. Good. So there's the header, and here's the code when we're using constant subscripts. We're going to have a variable called count, which is set to 0, and then we have 4 if statements. So if the 0th position is equal to contains the value or is equal to val, increment the count variable. And equally, do the same thing for position 1, do the same thing for position 2, do the same thing for position 3, and then return the value. So constant subscripts is the first version. That's why it has to be list of 4, not list of n. And 4 is convenient. 4 is not so too large that they can't sort of, do this. Furthermore, when it's introduced, there's always a little trace table. So when we first introduce this, we trace the code. I haven't shown you, what values are actually in list and what values in val, but that could be understood. And so, we do talk about having the students trace this sort of code so that they understand it by tracing it. Right. I'm glossing over a lot of things, but then here's the clincher. So we've gone through this one. This was my example of count element, and that's one method, one of 13 that's inside this class called list of 4. So count element is one of them. It's listed here. That was the one we did on the previous slide. And then there's the start of them. I sat down one day and I tried to come up with as many simple things that we could do on a list of 4 integers as I could come up with. We can copy it into another list. We can find a value when the values are unsorted. We can put a new value in the first position, put a new value in the last position, look for the smallest value, and so on, blah, 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 blah. And I even have a 2-string method. Okay, I'm not going to show you the code for all 13. That would be pretty mind-blowing, but give the students the code for loops. This is not like I show them this one and then I say, now go away and write 12 other pieces of code like it. I give them this code. And we do, I may not necessarily discuss in lectures all 13, but I do provide written materials and even some recorded videos sometimes for all 13 methods, and I trace all 13 as I introduce them to the students. Right, and about 2 weeks after they have that lecture, they go into a lab and they must correctly implement all 13 methods. Yeah, so code of this type for count element and similar code for the other 12, all using constant subscripts because that's all they know at this stage. And here's the clincher, it must work. They must get all 13 right. It's an automatic submission system. They find out immediately whether they got it right or wrong. So they walk out of the lab knowing whether they got it right or wrong. And it's not such a big drama if they don't get it right, because this is about like week 5 of the semester. Okay, you got it wrong this week. Don't worry. Come back and do it next week. And you can have as many attempts as you need to get this right. Now, there is a cost to having to come back next week, which is there's now a lab test every week, and eventually you must pass all of them by the end of semester. So you're starting to sort of compress the amount of time you've got to do all the tests, but that's okay. It's not a disaster. Just come back next week, study some more between now and then, and try again. So yeah. Then what happens? Second version of list of 4. We've done that one with the constant subscripts, and now I introduce a new version. I won't show you the header and so on. Now we have a variable called I, so that now instead of 0, 1, 2, 3 explicitly, now we have a variable called I, which is initialized to 0. And then after each one, we increment the value and find the return count. And of course, we have a trace table so we can see how this works. We talk about that. How do I sell this to students? It looks, I mean, this is easier, isn't it? Why are we bothering with all that more complicated stuff? Well, one of the selling points I say to the students is, suppose you wanted to modify your code so that it maintained a list of 100 elements. Well, you actually don't have to change any, you don't have to write any new code. You just copy and paste this as many times as you need it. That's kind of nice. That's the justification I give the students. But I mean, the real justification is I'm introducing the concept of using a variable as a subscript. And furthermore, I'm doing it in a context where there's no loop involved. So I'm sort of breaking things up into nice manageable pieces for them. Right, and then of course, there are 13 methods, just as there was before. And by the way, when I'm showing them this, I mean, I might have sometimes in the lecture, I might have this code side by side with it as we compare the two and see how they work. And so we do that. And then, of course, that was count element. And then there's 13 of those. Just as there was a copy list and a find unsorted insert first for the first version, there's equally versions for those. And again, I give the students all that code. I don't necessarily go through it in lectures, but there will be supporting materials for every method if they need it. And then a couple of weeks after that, so we're getting to about week 7 or 8 of semester, I can't quite remember, they walk into a lab and they have to do a lab test where they've got to implement things this way. And again, it must work. But if no dramas, if it doesn't, come back next week and try again. And then finally, I'm going to cut that short a bit. You're getting the idea now. We introduced versions of count element and the other methods, 3 and 4. Now we finally introduce the loop. We say, look, I say to them, what was the initial value in 0? I say, the initial value in I, or 0. And what did we do after each assignment statement like this? We incremented it, okay. And we did it how many times? Well, we did that the number of times that we've got elements in the array. So when I write the code to still do it on 4 elements, we initialize it to 0. That's what you just told me when you looked at the version I just showed you. We increment it each time around and we have a test. We stop after the right number of times. So that's the version 3. And then version 4 is the trivial change where I replace 4 with list.length, and now it works for everything. So I've broken up introducing arrays and certain algorithms on arrays into a series of tasks that build their way up. And at each stage, I'm insisting that the students reproduce that code in the lab, and a lot of code, 13 methods. And of course, they must get it right, must correctly invent all 13 methods. And that's a taste of it. This is what's called a killer plan, by the way. I showed you the Khan Academy thing a few moments ago where he talked about mastery learning. Killer plan is kind of mastery learning, but it's slightly different, and I won't go into why. The killer plan is nothing new. In the paper, it's reference 12, and reference 12 is for your convenience here. So it's a paper written in 1968. So it's a self-paced process. The essential element of a Keller plan is that the student needs to, that you need to understand, is that the knowledge to be learned is broken into a sequence of units, and students must pass a test on a unit before that student is allowed to move on to the next unit. And the student may attempt a test for a unit as many times as required. So I've implemented a Keller plan. Video lectures so that it's self-paced, so on. Now, this didn't occur to me until I'd done it, but it now seems so obvious. I'm astonished I never figured this out. In Australia, we're heading into flu season, as you probably are in South Africa. This line's showing you the frequency of flu in Australia, assuming that this year's flu season is a normal season. It may not be because of COVID. This is a diagram from before COVID. So around about the time, I don't know exactly when your semesters start, but around about the time when our second semester, our spring semester starts here in Australia, flu season is really starting big time and continues, is running pretty rampant mid-semester and is running all the way through semester. And unsurprisingly, there are students who miss classes because they're too sick. And it never occurred to me until I did this. I only found this out when I started talking to students. There were students who were missing 1 or 2 weeks, and they'd come back and they'd catch up. They'd talk to me about how they were able to catch up because of the nature of this Keller plan. And it occurred to me that for years I've been teaching students, and a percentage of them had probably been failing just because they'd missed a couple of weeks because of illness. But before we started making videos and all these other things, the relentless pace of lectures meant that if you missed 2 weeks of lectures because of illness, you probably weren't going to catch up. Mundane, but I was just astonished at how I'd never figured this out, frankly. Now, one of the things you'll be worrying about, I give them the code for all 13 was given to the students, then I insist they must make it work. Am I boring the students to hell? I mean, surely the students want to be creative Picassos, don't they? Well, yes, some of them do. By the way, what I'm talking about here is what you do to get a bare minimum pass in the subject. I'm not talking about what the Picassos and the watercolorists do. They do quite normal sorts of activities to assignments and so on. But am I boring the students by making them all do this? Apparently not. This is the one key. There are about 10 questions on our end of the semester survey, but I can tell you that the university management only care about this one. Overall, I'm satisfied with the quality of this subject, and you'll find here that for this subject, the way I'm teaching it with the Keller plan, 59% of students strongly agreed, and 25% of the students agreed that they were satisfied for a combination of 84%. Now, I don't know what it's like in South Africa, but first semester programming subjects at most Australian universities do not get an 84% positive record out of the students. So they're pretty happy. As the person was saying earlier who asked a question, a lot of the unhappiness that a lot of students have is because we ask them for assignments to write large programs and they can't do it. I mean, what could make you more unhappy and less motivated to study programming than being presented with a task to write a program and you don't have the skills to do it? Here I'm giving a student something they can do. Now, but it still might be setting off alarm bells, and that's fair enough, because on this quick introduction that I'm giving you, this sounds an awful lot like rote learning. I'm giving the student codes for various methods, and then I'm asking them to reproduce it in the labs. And yesterday, the legitimate concern is that the students won't generalize from the code. Now, let me back up for a second and say, try to say pithily, I am trying to get them to generalize because I'm giving them not one method, I'm giving them 13. And what I'm trying to do in my teaching is to get them to see what's similar across all the methods. So in that sense, I'm trying to generate it. But I agree that it's not obvious that it's going to work. Now, yesterday, Roxanne talked about the problems of having students memorize code. If Roxanne is listening, by the way, don't worry, Roxanne, I'm not about to diss you. I was very happy with everything you said yesterday. No problem. But I just want to make a connection in this way that yesterday Roxanne said that there were real concerns about giving students lots of code and asking them to memorize it, whether they'd be able to generalize to new cases and so on. Absolutely legitimate concern about what I've described so far. But all I'll say is that every method of teaching can be done badly. And as Roxanne was sort of saying, it is possible for a teacher to do pair programming badly. And she offered up some very nice techniques to stop that from being a bad process. Equally, what I'm suggesting to you here, where students are given code and they have to reproduce it in a Keller plan, that can be done badly, and it can result in students doing all sorts of bad behaviors like trying to rote learn the code. It can be if you do it wrong. You have to work at making it right. I can't give you a long version of how I try to make it right. And I'll say, in a sense, this is where the education research stops and the art of teaching begins. I have never suggested that all teaching can be reduced to research level questions. There's still a lot of art in my teaching, and there always will be. Well, if I ever teach again, there always will be. So let me try and hint at the good things you can do. Well, the pre-tracing student can't do these things, so let's not talk about them. You've got to sit down with those students and get them to trace code and get them to improve their tracing before they can productively learn the pieces of code I'm giving them. Now, the students who can post trace, they're not a problem either. The interesting students are the tracing stage students, the students who can only trace but don't see the abstractions. Those students, if left to themselves in a bad teaching environment, will attempt to rote learn the code. And we've got to stop them from doing that. Well, try to stop them from doing it. As I like to say to people, you can lead a horse to water, but you can't make it drink. And you can lead a student to learning, but you can't make them think. In the end, you can do all sorts of good things, but in the end, the student's got to make a decision they want to learn something. So we've got to stop that happening, the rote learning, and we've got to have conversations, teaching interventions with students that stop them from thinking about this as a rote learning exercise. So I have all sorts of teaching moments with the students where, our task as a teacher is to lift the student from this tracing level way of approaching the questions to a post-tracing level where they see the abstraction. And as I've written down the bottom here, a mantra that I say so often during semester, the students start teasing me with it by the end. I keep saying to them, remember the pictures, not the code. Before you go to the lab test, you should have a strong mental image of how the algorithm works. And then from that, you work out the code. You don't memorize the code. But to the stubborn student who doesn't buy that, the tracing student who may attempt to rote learn it, I have teaching moments like this, particularly when they've made their first attempt at the lab test and they've failed. Well, let's say, no, before they get to lab test, I've said, okay, you've rote learnt one method. Congratulations. Are you really going to rote learn 12 more? Because the trouble with rote learning in this situation is rote learning one method doesn't do anything to help you rote learn the other methods, the other 12 methods. Yeah, when you rote learn, everything's a special case. So, and then the other one is, which is more productive when a student has failed the first lab test, I say to them, look, you didn't get it to work. What are you going to do? Well, halfway through the lab test is when I often will have this discussion. It's not working. Okay, you couldn't remember it right. Okay, what are you going to do now? Random permutation? And one of my little spiels there is, well, random permutation can work pretty well. After all, 4 billion years of evolution produced us, but it did take 4 billion years. All right. You don't have 4 billion years to get your code working. Let's have these sort of conversations with students to try and bring their thinking around to the right way. And finally, I think this is just about the last slide. And I sort of complete the circle in a way with this slide. I was very happy when I realized I could write this. Yeah, I'm saying to the students, I said here at the bottom, remember the pictures, not the code. So much do I say it in class that the students start teasing me about it. I start to say it and they finish it for me. And I'm thinking to myself, now I put on my researcher hat and say, well, I should evaluate this sort of thing in my exam. And this could be a 5th trip around the research cycle. If I did it, chances are I won't because I'm enjoying retirement too much. But it could have been the 5th trip around the circle if I hadn't retired. And for that matter, maybe you can do the trip for me and tell me what happened. Tell me about the sights you see as you make the trip. So here's the idea. If we really want students to remember the pictures, not the code, how about this then as an exam question? And therefore as a research study. Here's the question. Here is some code we studied in lectures. You could also give them a piece of unseen code, but let's start with the idea that they've seen the code already. This code, and then we tell them what it does. I don't know, it counts the number of elements of the array, it sorts the array, I don't know. Then we give them the code. We give them the code. We're sort of inverting the process. Usually we tell students what we want them to write and they write it. Here I'm saying give them the code and then say, waiting for my image to come up. Come on, here it is. Coming up. PowerPoint's letting me down at just the crucial moment. Then the question is, using words and possibly diagrams, explain how this code achieves what it does. Probably an application level question, by the way, Bloom level application, I think. Analysis, Bloom level. Using words and possibly diagrams, explain how this code achieves what it does. So I was asserting in the last few slides that what I wanted to do in the teaching by giving students lots of code was to get them to abstract and start to see the pictures, start to look beyond the code. Well, really, I should test for that in the exam. And it would be a good way of finding out whether it's working and how I should improve things, if I should drop this idea or try it and modify it in some way for the following semester. So I should be putting, or if I'd been still teaching, I should have been putting questions like this in my exam to find out. But I do look forward to reading your research paper when you do ask questions like this. I hope somebody out there will try it. And I think that is, well, the end of talk 4. There you go. That's it. Thank you very much. I'm going to back up and leave that there just for a second. I've finished and we still have a little bit of time. So organisers, please,
Yes.
What would you like to do?
Questions, Prof. The first question is this approach that you used, is it the objects first approach? That means you first introduce objects before you introduce the rest, or other way around?
Yeah, good question. Our approach is, what some people call objects light. That's a curriculum decision made by the university. But I'll say, so we do introduce objects, classes and objects. And this is a class. It's implemented as a class where the thing that lives inside the class is a list of 4 elements. And then these are the various methods that work on it. So in that sense, it is OO, very, very light OO, but it is OO. It's done in an OO context. But it is very much, it remains, our focus is really on the methods inside the object. So in some sense, you could say we are procedurally, not exactly still heavy, but we're heavier on procedural than we are on objects. Would I do the same thing for objects? I'd have to sit down and think about whether it works. It would work for an objects heavy kind of approach. So I don't know is the short answer, I guess.
Yes, thanks. That's the answer. And then there's a question, where would they get these 13 methods you referred to?
Where would they get them from? I give them to them.
You send us an email.
I'm sorry? Oh, would I give you that? Is that the question?
Yes. Yes.
Okay, I'll be very happy to. If I don't think to do it myself, please remind me to do so. I'll be very happy to share all this. In fact, I used to give it to the students as a hard copy handout in week 1. It has all the code for all the methods, all in hard copy. And I called it the subject is called Programming Fundamentals, so I called it the Programming Fundamentals Colouring In book. And maybe I'll send you that because it does. Well, we'll see. I'll figure out something, but I'll be very happy to share any of these things with anybody.
Thank you very much, because I really think that people enjoyed it so much, what you said, and it is really a good approach. I can see it's a very, very good approach, and it can really help. So it is important that we look at all these things when we introduce the changes in the programming in future in our university. And I think a lot of the teachers and the Department of Education is also going to look into that to do it in future. Yeah, I just want to ask, is there anybody else with a question that was not in the chat box? Unfortunately, Bertie just had to leave for a moment. So if you send an email to Bertie with a question, can you just put your hand up and repeat the question here? I don't see any other questions that we've got now. We say thank you very, very much to Prof. Lister. We really, really enjoyed what you've learned to us, what we've picked up from you. And with this, we must say, like you see, with all the hand clapping and the thumbs up, everybody really, really enjoyed your presentations. And we look forward to working with you again and bringing you out to South Africa, that we can have another webinar series in future in South Africa. I really think it will contribute a lot to the research in South Africa and working together with you in future research in this environment. I think you triggered a lot of the people that never thought about this research. You triggered them to really do research in this environment and see how we can make it much better for our students. We really appreciate it, and we say thank you very, very much. And I ask everybody to clap our hands for Prof.
Thank you very much. It's kind of you. Thank you to all of you. I think, as I may have said before, I spent most of some of you are in the same situation as me. I spent much of my career in environments where teaching was a secondary thought for most academics, and sometimes I got a bit lonely and frustrating in that environment. So it's always a pleasure to meet people like you and to chat about this stuff. So thank you.
Thank you very, very much, Prof. If there's no other question from the people, I think we're going to take just a break until 12 o'clock here. That means a 15-minute break, and then we will start with the next session. And now we're going to talk to a lot of the people here. It's hard when we got a teacher now presenting. That means a person that must present from the school environment and the school's perspective. But we will get back to that at 12 o'clock. We'll just have a break now for 15 minutes. Sorry, Ronnie, I see you've put up your hand. Do you want to say something?
Yes, I was just wondering if I can quickly have a discussion with Raymond.
Yes,
the answer is yes, Ronnie.
You can have a discussion, yes.
Okay, super.
Yeah, sure.
Let me just quickly.
Yes.
Okay, so let me see. I need. My teaching aid as well. So this, I don't know if you know about Snowden's Cynefin model for managing different scenarios. They developed this some years back, and me and a colleague adapted it to teaching and learning as a management model. So what is happening is in this scenario where the student is confronted with something new. So this can be seen either as from the teacher's perspective or from the student's perspective. So you need to shift hats according to what's happening.
Mm-hmm.
But when you are confronted with a scenario, you end up in the middle here, which is called the position of disorder. So you don't quite know what's going on, and you have to make some kind of evaluation. So then you go into one of these modes where you now are kind of searching for familiar elements in terms of your perceived stimulus, if we can put it that way. So what are you confronted by? And then because it's in the familiar, it's in this area of known. So this diagram basically works in this quadrant, whereas we expand it to also cover 3 others, which I will talk to just now. So the procedure here is to sense what's going on, then to categorize it, and then to respond. So in this process, when the student then finds this familiar environment of somebody mentioned earlier, recipes or best practices or standard procedures, we then decide which one of these is then the best one to apply to the current classification of the problem. So this is kind of a cause and effect. So the cause and effect is quite known. So it's standard way of addressing it. And then once we then make the selection of the abstraction here, we then can solve the problem. And when you operate in this quadrant, it's more about the procedural fluency of things. So how quickly can you address this scenario? But it is kind of restricted to very well-defined problems. So the moment that these kind of problems that the students are presented do not fall into the well-known area, it's then when we kind of move into one of these other quadrants where you don't know what the solution is. There is no best practice to kind of say, what should you do? What is this classification and selection of abstraction? So depending on the skill level, so this is mostly for lower level, where the student, as I say, presented with well-known problems. In this case here, you kind of move to those upper levels of Bloom's taxonomy, where now the student is kind of required to come up with their own kind of solutions.
Yep. Mm-hmm.
So in this case, for the chaotic environment, it's basically serendipitous kind of learning environment where you stumble upon the correct solution. It's that one which you described as the student try, and then eventually they come up with some kind of a solution that kind of addresses the problem. So that is this environment. And then the one which I try to get my students to work in is where they are in a fail-safe experimentation environment where they probe, sense, and respond. So the cause and effect is only known in retrospect. So you do the experiment and then you see, okay, so this is how this thing is working. And then hopefully someday in industry they will work in this area here, where they kind of go into the critical thinking, where they analyze and synthesize and all of that. But most of our students don't get to this level. It's only at postgrad level, maybe, where they start operating in this scenario. And then you go full circle. Once you've made some new algorithm, it then becomes known as part of your best practices, and you back full circle to the beginning again.
And so I can see how you're particularly in a sort of a problem-based environment, learning environment. You're trying to move the students in a clockwise direction around this in a constructive way. So yes, you might expose them to a certain amount of chaos, but that's good. That motivates them to learn, and then you manage them with this, as you say, the fail-safe experimentation in the complex stage, and then it moves around and becomes knowable. Okay, good.
Yeah.
I like that as a description of how teaching can proceed, particularly in the more towards the end of degrees. My specialty was really the early years, first year, a lot of it, and I am a little bit possibly overprotective of my students in those very early stages, but I would not. Yeah, this is. I wouldn't say it was wrong to do this at any stage, but it's particularly suited, I think, to the latter stages.
Yes, yeah, no, definitely. So I just wanted
it's nice
to.
If you're able to relate it to Bloom.
Yeah.
So where do you work, Ronnie? Are you at the university or
I'm
schools?
Working at the same university, Tshwane University of Technology. I'm just in the engineering department, and I'm tasked with teaching engineering software design. Have been for many, many years, and due to the high failure rate, my pass rates are like 20% or somewhere around there. I have made it my mission to understand why students fail, and this is part of my research that I've done.
Good. Oh, it's great that you're approaching it with a research mind, because, as I sort of talked about in earlier talks, you can approach it in less healthy ways. It can be very dispiriting sometimes to have students not apparently learning and so on. But if you approach it with that research mentality, that's great. There's always the optimism that you'll figure this out. It's good.
Super. Yeah. Thanks. I would like to speak to you at some stage some more offline. Maybe collaborate a little bit.
Okay, that's quite possible. I mean, very positive. I just want to warn you that I'm now retired, so I'm not necessarily the most reliable guy. In one sense, retirement is great because you have more time. In that sense, on the other hand, I also don't like to get stuck in a situation where I have to do something non-trivial by a certain deadline and so on. So you might find me evasive about committing to doing things, but I'm happy to talk at the very least. And if what you're talking to me about sounds entertaining, then I might roll up my sleeves and do something serious.
Yeah, no, I do understand. Same for me as well, as I've got many things that I need to attend
absolutely. To. You're more time constrained than I am if you're working, still working.
But thank you. I really enjoyed your discussions, and I think that for certain I will try to implement some of it into my courses as well.
I'm glad, given that you teach at the other end of the degree, so to speak. I'm pleased that you can see some connection to what I've been talking about.
Well, I'm actually teaching. It's a year course, and it's the first time that the students are exposed to programming.
So okay.
So it's on the low level that I'm actually teaching, meaning that it's introduction to programming, and then in the second semester we do a little bit more advanced things. So the first semester it's a basic introduction.
I didn't realize how lucky I was when I first started teaching, because I actually taught the second semester, and I was following somebody who did a really good job of teaching in first semester. It was probably the happiest teaching times in many ways, because I was getting good students. Students already knew solid stuff, and I could move them on. And then I took over the first semester and realized how lucky I had been.
Yeah, it's quite a nightmare to get them to understand, yeah, and to write purposeful code, not
Absolutely.
just duplicating what you've taught them in class.
Yep. Anyway,
Thank you
I
so
need to
much
take
for
a
your
short
time. I
break
really
before we start.
appreciate. Yeah, I
Oh,
really
it's been
appreciate your time.
a pleasure to talk about this stuff. So I'm going to take a short break now before we start again. So nice talking to you, and we'll talk again.
Super. Have a nice
Okay,
evening.
bye.
Good afternoon. Thank you, everybody, that we're back. I'm very, very glad that we did get some of a discussion between Ronnie and Prof, because that was also very, very interesting. And seeing that is more on the way we approach, another approach to programming. The next speaker is Edward Fair. I hope I pronounced correctly. And he's a CAT and IT teacher at Mpelisweni Secondary School in the township Katlehong in Ekurhuleni. He's got very, very good results in his IT learners over the past few years. That he got a 100% pass rate there. He says about his school is about 2,100 learners, but the school capacity is only 1,200 learners. So that we must understand, it is a very full school. And the reason why the school has got so many children is because the school has got exemplary matric results. So Mr. Fair's got also coming from, got a diploma in IT and a BC in biochemistry, very interesting. And then he did his postgraduate education certificate at UNISA. He also completed A+, N+, MCP, MCSA, MCSE, and MCT. We're very, very glad that Mr. Edward can talk to us, and we're really going to enjoy to find out from him why they are so successful in their school, that they get so many learners that wants to study in their school. Just feedback for the people coming from other places. The rural schools, we normally got challenges, and also in township schools to learning students IT. Maybe Edward can also tell us what the experiences having computers, access computers for the learners, etc. What are all the challenges they also have to cope with? Thank you very much, Edward, and we really look forward listening to you.
Good day, everyone.
Thanks, Edward.
Oh, okay. So thank you for this opportunity. And I also would like to thank all the organizers and my facilitator, Tanya, for giving me this opportunity to present today, and also for her support, her guidance, and the knowledge that I've learned through her, and also the other facilitators that guided me through this path. I don't know if I can just share my PowerPoint presentation.
Yes, please.
I don't know if it's visible there.
Yes, we can see it. It's very nice.
Oh, okay. Yeah, like I said, thank you once more for this opportunity. I'm an educator at Mpilisweni Secondary School, and I've been teaching IT and CAT for the past 12 years. Yeah, Mpilisweni Secondary School is a township school in Katlehong, in Ekurhuleni. So the capacity of the school is 1,200, but now we have 2,069 learners currently. And most of those learners come from disadvantaged homes. And we are involved with this feeding scheme and also the sanitary pads that is given to girls as donations. And then the school offers CAT and IT. We have 2 computer labs. We have the CAT labs that can accommodate 40 computers. We also have the IT lab that can accommodate 30 computers. Now we are using the Delphi 2010 and the Microsoft Office for CAT. So I can say 95% of the learners don't have any computer at home or any form of computing device at home or even cell phones. So they actually rely on the computers that are at school. Now, in terms of the mitigation plans, because now we got more learners this year than previous years, and so the school has bought some mobile classrooms so that we can accommodate the high influx of learners. And then also the school makes use of scholar transport because some of the learners come from different locations. So the scholar transport is necessary to bring them to school, more especially those that are interested in CAT and IT because they have to travel from different locations to get to the school. And then also the GT has employed additional educators. Then we also have the Presidential Youth Brigade that assist also with the functionality of the school. And also most of the learners are given food packages, especially during the holidays, like now that they went for holidays on last week. And then also we have patrollers who work day and night to make sure that the school is secure. Now, the school will be transformed into an SOS, a specialization for IT. So the district director is busy with all the planning, and also on our side, like even today we have welders who are already doing the measurements to start transforming the school. So we'll have new classes because in 2023, there will be an introduction of digital technology in grade 8 so that we start to do coding and robotics in grade 10 as well. So in that aspect, we will be grateful if we can also have some sponsors to accelerate the project. Now, in terms of our results, you can see that in 2019, we were having 183 learners and we got 79.8%. But fortunately, I don't know whether to say fortunately or unfortunately, during COVID, that is the time where we actually got more in contact with the learners because we were given a short time and we had to utilize that short time perfectly, and that is when our results started going high. We got 92.2%, and we had 153 learners. So last year we had 249 learners, and we got 96.8%, meaning that as COVID started, our system, our planning changed, and now we got more learners, and the results has been improving. That is why this year we have 352 learners currently in grade 12 who are going to be writing their matric exams this year. And also the number of learners in the school has as well increased. Now, in terms of IT, like I said before, we have been getting 100% since ever since I started in this school, and the participation in IT, or the number of learners doing IT, depends on the number of computers that we have. So, but I will explain further when we go to the next slides, because in 2019 we had 27 learners, 2020 15. So because the IT lab can only accommodate 30 learners at a time, then there are some changes that must take place so that we don't have more learners doing IT whilst the computers or the resources are not there. But for CAT, we have more learners because also sometimes they come into the IT lab as to use the IT lab as well. So this year we have 32 learners. In CAT, we have 112 learners who are doing CAT this year in grade 12. Now, I will start with the focus questions. Number one is, how do you make learners do and love IT? Now, the teaching IT, it may look easy, but as an individual, you need to be passionate, you need to be consistent, you need to be determined, you need to have some of your good qualities before you can start anything. So like when I go to grade 10 for my first class, because in grade 10, it's their first time to do IT and everything is new. They have never, even when they did technology in grade 8 and 9, but that technology, yes, there is that part of input, output, and processing, but it doesn't go into IT. So in my first lesson, I always make sure I give the definition of a computer, but I don't expect them to know that definition. I'm only interested in that part of electronic device. So if I know a computer is a programmable electronic device, I focus on that electronic device. So immediately I give the definition, I tell them to return the word electronic device. Now, I will then ask each learner to tell me what is their career choice, because in grade 9, learners make a career choice before they take the subjects that will help them to go through that career. So when I ask, okay, what is your career choice? You will hear some says, I want to be a doctor. Then I tell them, in medicine, you also have devices that you need to use. You need electronic devices to use, like those scanning machines, those thermometers, all of them are coded devices that you use. So you need the help of an IT person to make devices that you'll use in your medical field. Now, I also get some learners say, I want to be a traffic officer. Then I say, even with the traffic officer, you have speed cameras that are on the way. So those speed cameras, they are coded to measure the distance that the car is moving. Then others will be saying police officer. So different careers. Then I'm able to tell them, even in the police, you need to capture reports, you need to type information or some reports. So you still need a computer wherever you go. So my aim in that first lesson is to make sure that all learners must know that whatever you do, you need an electronic device. Even if you want to be a teller or work in the restaurant, there is still a form of electronic, a POS or something that you need to use. So you cannot isolate IT from any career that you want to do. So that drags the attention to say, yeah, everything I want to do, I need to also have IT in it. So that's the first phase where I get them interested and hook them to love the subject. And then now I'll ask who wants to be the programmer, the one that wants to program all those devices that will be used in different fields. Then I find now some few learners will raise their hand. No, Minera, I want to be a programmer so that I will be the boss. So now we clap hands for those ones because now it's like they want to be the boss. They want to be the ones that will define every other career. So that's the first aspect that I use to make sure that the IT becomes the core of what they are thinking, apart from the career choice that they have. Even if it's accounting, they still need a bit of IT there. So from there, I need now, like for instance, like I said before, we have 30 computers in the lab. Like this year, I have 34 learners doing IT in grade 10. Now, of the 34 learners, it means 4 learners will not be able to use the computer when they come to the lab. It means that I need to get these 4 learners to be what I call my peer, the guru learners, the lab assistants. They must be the ones that will help me push the IT through to the other learners. So which means because the learners don't have computers at home, I make sure that the lab is opened in the morning, it's open during lunch, it's open after school for those few learners to be able to have the knowledge faster than the rest of the learners. So they're always in the lab practicing with me. I show them some of the skills faster before the whole class because I need them to move around because it's more of learner-based learning than the teacher-centered learning, so that it gets interesting and the knowledge is easy to get to each learner, because it's easier for a learner to ask another learner than to ask me sometimes. So that's how I get my guru or my lab assistants. And then those lab assistants, they assist me with switching on and off the computer, so they get the basic knowledge of how a computer works. Even some of the computer components, they see it before the whole class can see it. And then they also check if they are able to also first know how the mouse is connected. And sometimes most of those learners are learners that already have seen a computer before, or they have a sister or someone or a brother who is using a computer. So the knowledge is easily spread when I use them, because if learners have to share a computer, it means one learner or 2 or like 4 of those my learners will not be able to use the computer, and like that for a month or 2 months they will not even know how to use the keyboard and the mouse. So it will be a challenge when they have to write a practical test. So that is why I use this aspect of getting a peer mentoring learner that will assist in making sure that the knowledge is distributed in time. And also they are the ones that will motivate other learners to come to the lab, because they will be telling them, no, come now, I need to go and show you what Miner taught us. So it becomes easy for other learners to join them during lunch or after school in the lab, so that they can all practice together. And now my lab assistants or my guru learners, they also have that responsibility of discovering new codes. They must try different things, because at least they know how to use the computer. They know when a computer is switching on and off, what they must do or something. So they have that idea already, so they use it. And these peer learners, they are in grade 10, 11, and 12. So sometimes I mix them together with the grade 12 learners as well, so that they get developed quicker and easily for me so that I can use them for my classes. Now, how do you introduce programming to novice? So the introduction of Delphi programming is not always easy, because everything, it's not like Microsoft Office or Word or Excel. It's a program that has got many different aspects, many components, and other different sections that you need to know about. So introduction to the GUI, it's fairly easy. You just open it, but then I always start with the robot, because it's an interesting topic. It's motivating, it's attractive, it's interesting, and learners can actually see the traffic light on the street, so they can see that what I'm doing now is exactly what is on the street. So it encourages them, it pushes them to want to do it, because they can see that, yeah, this is how it looks like on the street. So if I do it on this computer, it means that it can be taken, it can be used as the one on the street. So it's, for me, is the first aspect. And through these, many lessons are learned, like knowing the components, knowing the naming of the components, and they also see how to search, because Delphi 2010, now you have to search for some of the components. So the different aspects of manipulating through the GUI becomes easy, and they have an understanding of what is happening there, and the program on its own is also interesting. So that is why I use this first the traffic light as my first project, to make sure that it gets them glued. Now, my Guru learners will go far, because the grade 12 learners now know how to put timers and make the robots work with the timing. So they will learn that from the grade 12 learners or grade 11 learners, and also now teach these other grade 10 learners behind the scenes, so that now, instead of just putting code on the red and yellow button, they will put the timers to make the robot actually work as it is on the street. So it also makes it more interesting. And through that, most of the information that I need them to know is already there whilst we move into the other lessons. So, and also learners will learn to use the keyboard and the mouse, because basically most of the learners, I can say 90% of them, is their first time to touch a mouse and keyboard. So they will learn as well to type everything using the keyboard, or to double click or right click on a mouse or left click. They'll learn how to use the mouse and get familiar with all the devices that they need. So it's, for me, it's something that has always worked, and even now it's still working for me. And then, how do you maintain and improve performance? Because that is the key thing. Just like Professor Raymond Lister said, when learners fail, the first finger is pointed at the teacher. So you, as a teacher, always you have to make sure that learners don't fail, and if they fail, it shouldn't be something different, not that I was there and then they failed. So the first thing I noticed was the language barrier. Most learners have challenges with English language as a language of teaching and learning. So it means that if I make use of question papers only, learners get familiar to the different aspects of questioning and different aspects of what they expect in an exam or in any assessment, then it makes it easy for them to actually pass, or to actually understand most of the concepts. Because in reality, most IT questions are scenarios or examples that are from real life. So it becomes easy for them to understand that way. And also, I have what we call the TADR, teach, assess, diagnose, and remediate. So when you teach, you have to assess. And as Professor Raymond Lister said, a good exam should teach you something new about your students, or about your learners. So when I assess them, I should be able to learn something new from that exam, and also learn what they know and what they do not know, what I need to emphasize. That is why I have to always teach. I must assess all the time to make sure that they are understanding what I'm teaching. And then I must diagnose to see which aspect is it that they don't understand. Then I must be able to remediate. I must be able to fix that aspect, so that they are able to succeed in the next exam or in the future. And also, for me, it's also another way of making them understand the IT itself, so that even if it's in real life, let's say they are not going to school anymore, they face it in the workplace or wherever, they're able to remember and use that IT knowledge effectively. Now, so yeah, my dream is, it has always been to make sure that all learners in the school live with IT knowledge. They mustn't leave the school without having a knowledge of IT. So I'm happy that the school is going to be transformed into a school of specialization in IT, and all learners will be able to have IT knowledge before they leave the school. And because of the fourth industrial revolution as well, IT is almost everywhere. So when they live with a computer knowledge, it becomes easy. Now, my personal dream is to make sure that learners, depending on their capabilities, should get something based on what the level is, because we cannot all have good learners. We have the high flyers, those ones can be engineers, anything. We have the moderate learners, those ones can work as database administrators, network engineers, they can be nurses or whatever that is available for them. Then we also have the high risk learners, those that you can teach and then still they don't understand anything. But at least with IT being a practical subject, it means that they can at least learn how to open and fix computer components, change the hard drives, check the network, check if all the network cables are connected, just do basic computer maintenance, network maintenance, assistance. They can assist in different areas, even at the hospitals, we still have computers there. They can just be technicians just to make sure that they fix. So having the basic knowledge of IT from high school is very much important to make sure that we don't lose anyone along the way. Everyone must fit into the level of their capabilities. I think I'm done.
Thank you so much, Edward. We really enjoyed your presentation. And it is what makes my heart warm is the fact that you had so many challenges with infrastructure, everything, and still you go on and still you get 100% pass rate. So we're really proud of you. And I'm sure there's a lot of teachers also that is taking part in decisions today that can contribute to this and say, we've got exactly the same type of environment and we're also coping with that. And I must praise the teachers in our country that is really doing this in schools, because it is really challenging in schools. And like you said, when these robotic courses are coming, it is also going to be much more challenging. Before I close, I just want to know, is there any if there are any questions for Edward? I don't see anything in the chat and nothing here. So that means that is the last presentation, but there's one group of people that I didn't thank, and that is the Department of Basic Education with Karina and subject advisors that helped a lot to encourage teachers to attend this seminar as well. We want to thank Karina and the subject advisors from the schools for their contribution to this webinar, and I really think it is definitely going to was a big success due to their participation. I see Karina wants to say something. Karina, I give to you.
Thank you very much, Joey. From the Department of Basic Education side, we really want to thank you for this opportunity. We know that you are bearing all the organization and everything of this. We really appreciate it, and thank you for thinking of us, inviting us to join this wonderful seminar, and I hope it's not the last one. Thank you very, very much.
Thank you, Karina, and thank you for all your people's participation. Yes, it won't be the last one. We're looking forward to arrange one by the end of the year and bring Prof. Lister out to South Africa, that we can have face-to-face groups with him and webinars, that he can also go and visit some of the schools and see how it looks like in South Africa as well, where we do ICT. And he will see a lot of the things are the same. Some things will differ, but a lot of the things are the same. Thank you very much. If I miss somebody, I'm very sorry, but I say thank you very much, everybody, for the people that helped with the arrangements, the people that took part, that did the presentation, specifically all the speakers that presented for us. We learned from each and every speaker. We're very, very glad that you could participate. Thank you very much, everybody, and have a nice afternoon, and think about what you've learned and how you're going to introduce it in your programming subjects. Thank you very much, everybody. Karina, I see your hand still up. You want to say something else? Thank you very much. Then we will say that is the end of our sessions, and hope you've learned a lot from the conference. Thank you so much. Goodbye. Oh, sorry, I forgot one, and that is very sad. I'm so sorry that I said goodbye. All the people of the teachers training from TUT also, you also contributed, a lot of the people coming to the conference. Like we said, engineering and teachers training. I forgot, I'm so sorry that I forgot to mention that you also took part. Thank you so much. Chris, we can stop the Facebook as well now. Chris, can you hear me? Chris, can you hear me?